All right, once again, thank you very much. Appreciate everyone showing up to Earth Day 2024 event. And once again, we want to thank our sponsors, the Claire Freelander Foundation, and a special thanks to our two corporate sponsors for providing us our breakfast and our lunch, both Ainsworth and Thermal Systems Associates and Hisense. So thank you very much. Without your support, we simply cannot do these kinds of events and try to create the awareness that we believe is going to help scale for us to resolve this climate crisis problem. And one of the things I keep on hearing, I heard it last night again, is that we keep falling behind. You know, society is behind. We're producing way more. We're producing way more emissions. We're not building up renewable quick enough. And the way I see it is maybe a decade ago or 15 years ago, that was surely the case, right? Probably why my Twitter handle is doom and gloom. And that's kind of was my game. And I was really pushing that this is a climate crisis. And everyone thought I was a little insane to call it that back then. And now we're here. And what I've seen in the last 5 years is just a tremendous collaborative effort across all societies and all continents and all jurisdictions where energy efficiency and decarbonization, electrification are becoming not buzzwords, but they're really becoming the standard. And then here's ASHRAE developing multiple standards to help us get there. So even though we're still behind, I see us catching up. And if we can scale that, hopefully we can catch up quick enough and resolve what some of us think is one of the greatest threats that humanity has ever faced. So it'd be pretty cool to be part of that successful team. It would just be really cool. Thank you for the speakers earlier. They really kind of laid out the ASHRAE vision, what's happening with guidelines and standards that engineers and contractors and architects are going to be able to use in the future. And now we're going to get into the jelly and the peanut butter and jelly of the sandwich about what's getting done. I'm going to quickly introduce the 6 panelists. Just a quick blurb. Griffin Teed is in the carbon reduction group at JB&B. Sarah McLean is a team leader at WB Engineering, focusing on EV infrastructure. Richard Gerby is co-founder of Highmark in 2013. They specialize in heat pump technologies. Jeff Erlap from Salas O'Brien, who was actually introduced to us through Fordham University, so thank you, Fordham. Jeff Firm is a recognized leader in energy analysis and geothermal planning. And then we have Jean-Simon Venn from Brainbox AI. He is a technology expert specializing in the fast and efficient mitigation of technical innovations to commercial applications. And last, we have Randy Topp from Ainsworth. So thank you again for being our sponsor, Randy. And Ainsworth is a leader in building and energy solutions as an engineer, project manager, and a contractor throughout the Americas. So thank you all for attending. We're going to start with a longer presentation from Griffin Teed from JB&B. We're going to take questions. We're going to challenge him. And we have the panel to discuss, to provide answers from their diverse backgrounds. After Griffin's half-an-hour presentation, we're going to allow the other panelists to do a shorter 10, 15-minute presentation on their focuses. So it should be a diverse panel, and hopefully we're going to get a lot of different questions. So to begin, I want to welcome Griffin Teed from JB&B. Let's give him a warm welcome. Thank you, Griffin. Appreciate it.
Thanks, Scott, and thanks everyone for being here today. As Scott mentioned, I'm going to be going through primarily a case study at 520 Madison Avenue for a decarbonization study that we completed a couple years ago. But first, we want to talk about electrifying buildings and decarbonizing buildings in general and the challenges associated with high-rise electrification in particular. And then we'll go into 520 Madison. And then at the end, we're going to talk about some innovative technologies and strategies that we're using at the building and how maybe that'll be kind of changing the paradigm for New York high-rise decarbonization. So first, existing building decarbonization. What does that mean? How are we decarbonizing buildings? And I think we kind of already touched upon it in the earlier sessions today, but that really, when it comes down to it, is electrifying your heating systems and domestic hot water systems, moving away from fossil fuel sources in the boiler plant to air-to-water heat pumps, water-to-water heat pumps, other forms of heat pumps. And we have confidence that that leads to decarbonization in general because the grid is moving away from fossil fuel sources as well. We're adding more renewables to the mix. You saw the graph that Paul showed before, kind of increasing renewables over time. And in New York State in particular, we as engineers can have even more confidence because of the CLCPA, which is a law that requires 70% renewables by 2030 and 100% renewables by 2040. You can see our progress to date so far on the right side, which is really showing that we're getting pretty close to having a lot of projects in the pipeline towards that goal in 2030. I do want to address that there has been some challenges with supply chain and inflation costs recently that have led to some concerns around meeting that target, specifically in 2030. Maybe it's going to be a little bit later. But when it comes to an engineer's role in the larger picture, then that means that we need to be thinking of solutions that are more efficient and using heat pumps in a very efficient manner so that we're not being kind of hogs on the grid and taking a lot of power for one particular building, right? We need to be good players in the larger community and environment so that we're all able to kind of use these renewable resources at large from the grid and not put too much stress on it. But when it comes to high-rise building decarbonization, right, there's several different challenges, and I try to think of them as three different buckets. We have technical challenges, we have financial challenges, and we have social challenges. I'm going to mostly focus on technical challenges, as this is an ASHRAE presentation, right, and a conversation, but these all are really interplay with each other. They're all kind of connected. You can't think of them siloed. We can't be an engineer kind of working in a small kind of room right on the side and then come back and say, here's my perfect solution, but then it costs all this money and it disrupts everyone and causes a big problem, right? We need to think about everything connected together. And so we'll talk about that a little bit throughout the presentation. But the first thing, if we're going to go top to bottom, we're going to think about some of these things that were challenges specifically for 520, but it's true for any high-rise building. That rooftop space is at a premium. We're working in New York, right? We have tall, skinny pencil buildings. There's not a lot of rooftop space, especially for existing buildings. You have building maintenance units, you have cooling towers, you have tenant equipment. You maybe have an owner who wants a nice new amenity space on the rooftop, right? You're competing with all of these different demands in terms of trying to find locations for having these new air source heat pumps. So having any space there is kind of a premium. And really what drives the kind of point home further is that the amount of heating capacity that one air source heat pump can provide compared to a boiler, it's a much larger footprint. So if you're able to just kind of throw boilers on the rooftop of a building, it might be kind of easy actually to find space, but air source heat pumps, that's not the case. We have a much larger footprint to deliver the same amount of heat. So rooftop space is at a premium. If you can find the rooftop space, right, in an existing building, you might not have the power. And so trying to find the electrical distribution and the availability for power for that rooftop can be quite a challenge. And this can add to that financial piece, right? It's extra infrastructure costs, the social piece, how you're going to disrupt the occupants in the building as you're installing any new electrical service to the rooftop. These are all pretty major challenges when it comes to trying to figure out how you distribute that power to any new air source piece of equipment. At the same time, on a positive note, right, do want to mention that a lot of the studies that we've been doing, you actually see that the existing service capacity when the building was originally designed is actually sufficient. So when thinking about it from an electrical perspective, there isn't really that same concern that many people have, that we're not going to be able to have, add any heating for electrified heating systems rather, and we're actually going to have that power available just because the way the building was originally designed. So it's really about trying to find ways to locate power from the switchgear to this equipment downstream. But when you have all this equipment in place, right, so we have the ability to find those heat pumps, right, but it's actually not just a place and a location challenge, but it's also an envelope challenge. So many of you maybe are familiar with this, but in these tall, skinny pencil buildings, right, we have a lot of envelope heating loads, right? All along that surface area of the perimeter, we need to be able to heat in a very cold environment that New York gets to in the middle of winter. And so you can see here on the slide the changes in codes, and we talked about codes and how they've kind of improved energy and heating energy over time. But at the same time, these are existing buildings that have been built 100 years ago, like we were describing before from Paul's presentation, 40 years ago, 50 years ago, right? They're leaky, there's air infiltration, there's thermal bridging, there's all sorts of different issues that we need to address. And all of these different kind of problems in the envelope lead to really high heating loads on the perimeter. And the easiest way traditionally to address those high heating loads is with steam or really high temperature hot water, right? There's not really a lot of need to be able to radiate that heat very with additional fan-powered equipment or anything else like that, right? So it's a very kind of straightforward solution there. And that's not something that's really easily able to be addressed with heat pumps on the market today. So it's a distribution challenge too, right? How do we get those really high temperatures to the perimeter? This is an example from two different schedules from the original drawings that JB&B did, back in 1980s for 520 Madison. But we have steam preheat coils, and then we have 200-degree hot water design on the perimeter, right? Those are two really big challenges that most heat pumps on the market today and really kind of a traditional vendor is not really able to deliver. And you can see a selection from an example, water-to-water modular heat pump that we're looking at for 520. It's able to deliver 160 degrees. Other ones can do even only as much as 140. So this is another real constraint when it comes to thinking of how do we find these small modular pieces of equipment that can fit easily into the available footprints we have in buildings today. And then going from the top to the bottom, right, okay, well, what about the ground? How do we use the ground and leverage the ground to be able to provide heating to a building? Well, it's New York City, land's at a premium. We don't really have much space available for most buildings. There are some innovative strategies we're gonna get into a little bit later in the presentation. But generally speaking, land's at a premium. We don't have large office campuses throughout New York City. So thinking about all of these different constraints and how do we actually approach the problem, we try to take the strategic decarbonization approach, thinking of it as a three-step process where we reduce energy or heating loads, then recover energy or heating within the building, and then electrify at the end. And really the key takeaway here is we want to minimize heat pumps because of all those challenges I was just describing. Heat pumps are expensive, they take up a lot of space, and they're not really kind of quite there yet to be able to provide heating right now. So if we're able to try and address the problem right now because we don't really have an ability to wait 20 years for the equipment to kind of meet up to provide steam, we need to find ways to take this approach and be able to minimize the amount of heat pumps that we have to use at the end of the day for electrification. So we're not trying to walk into a building and electrify right away with heat pumps or electric resistance from day one. We need to take this kind of methodical, holistic process to figure out decarbonization for these high-rise buildings. So now I'm going to get into 520 Madison in a bit more detail. So 520 Madison, it's a 40-story building in Midtown Manhattan. It's about 1 million square feet. We'll get into some of the stats in a little bit, but before I do so, I want to mention the Empire Building Challenge. So this project was part of that with NYC. So this was it's a program. Won't get into too many details, but the program is really trying to accelerate and move decarbonization forward for high-rise buildings, specifically in New York State. So there's demonstration projects that are being installed across the city. I think you're going to hear about one of them a little bit later today. It's already underway. But they're trying to fund for technical assistance and implementation funding. And so 520 Madison received that technical assistance funding and then also the implementation funding as well. So this is cohorts 1 and 2. We were working with Tishman Speyer as Tishman Speyer owns 520 Madison. And so 520 Madison in 2019, that was the baseline year because when we did the study, the building was not really fully occupied and it was not clear how much energy it was going to be using going forwards. We'll say today it is kind of back to that occupancy levels we were seeing before, but back in 2019, the building was 100% occupied, and the primary tenants in the building are real kind of financial services. So we have headquarters for hedge funds, for all sorts of different kind of intense operations that are kind of really complicated, like I think someone mentioned before, financial research analysis, right? Whatever that means, I don't know. But they're doing intense operations with lots of computers and analytics. And so they require a lot of cooling, all that's to say, right? So cooling is kind of required really predominantly throughout the tenant spaces. And they're working after hours and all sorts of different things. So the building, you would think of it as kind of a high energy user overall. And while these numbers don't quite kind of meet the Advanced Energy Design Guide EUIs of a 25 or a 30, an 87 when it comes to a high-rise building like this, an existing building, you actually think of it as pretty efficient. From a lot of other buildings that we look at and other studies we've done, it's on the higher side, or the lower side rather, of efficiency. So it's an Energy Star score of 88, that's an A, right, and a LEED Gold certified. So The goal here was to take an already pretty efficient building and then figure out a way to move it into the next 40 years. So the past 40 years was spent making it very efficient, but how do we now decarbonize the building? As that's the real goal of today for the next 40 years. And so this is kind of an overview of the HVAC systems. And so we have two kind of different systems. We have the heating system on the left side. It's provided by district steam from Con Ed, right? That's that fossil fuel resource that we're trying to move away from as best as we can. And then on the right side, we have the cooling system. It's really rejecting heat throughout the cooling tower from a base building chiller plant, as well as any tenant water-cooled equipment as well. Something to note is that there's also ice storage here, and so there's something that we like to try to incorporate whenever we can is ice heating. I won't talk about that too much today, but that's another strategy, using that thermal storage and kind of unlocking that next step of decarbonization, which we were looking at the end here, but that's a whole hour-long presentation for another day. And so really want to highlight again that this building requires that higher temperature on the perimeter, and that there's these two different systems. We're cooling sometimes, and then we're heating sometimes, but we're not necessarily figuring out a way to lock those two systems together, create some kind of interplay. And of course, as we're thinking about these different strategies, we're figuring out the building, right, and thinking of what are the performance going to look like. We need to think about that in the context of a calibrated energy model. So the calibrated energy model we developed, you can see a rendering on the left side here. It's really calibrating to the monthly utility bills and becomes that bedrock for our analysis and the tool that we're using going forwards to say we have a lot of confidence in the different strategies that we're exploring as part of the study. And back to that slide I was showing before, the three-step process here is to reduce that energy, then recover before electrifying. And so at 520 specifically, as we're talking about those really high temperature loads required on the perimeter, we want to improve the envelope as much as possible. So there are a few different strategies here, and we won't get into those in too much, but they're really able to reduce the temperatures we need on the perimeter from potentially as much as 180, 190 degrees down to 140 degrees. And those are all their enabling steps that are helping that as well. So new infrastructure in place that's going to be able to help kind of move the building towards the future decarbonization. While it might not be a specific measure, it's more of an infrastructure improvement. It's really key and critical to kind of plan for over time. And then from that recovery step, this is a really key piece, especially as the building uses a lot of cooling year-round for those high intense operations. We're recovering heat before it goes out of the cooling tower and doing condenser water heat recovery. Something, again, I think is going to be talked about later on today, but that's a really key strategy to keep the heat inside the building, right? Don't let any BTUs escape so that we can do any heating that we need with the heat already inside the building. And then at the very end, electrifying, right? That's that last step. With any hand washing for commercial tenants in their office spaces, in the bathrooms, right? Doing it's the local heaters, so we don't need this kind of large infrastructure anymore and worry about any storage associated with that. And then from the heating perspective, it's air source heat pumps, ground source heat pumps, and that ice heating. So having those three different sources of heat to be able to provide heat if the building is ever in a thermal deficit and requires more heat from the outdoors. So these are the different strategies, but it doesn't really happen overnight. And so this is the flow diagram now. It's a lot more complicated. We have a lot more sources of heat. If you follow the yellow lines, right, largely we're trying to take that heat from the cooling towers, that condenser water loop, and inject it into the building system. It gets a lot more complicated, but this, again, doesn't happen overnight. We're not just showing up with this flow diagram and all this piece of equipment being installed immediately. So we have a carbon neutral roadmap. So the goal for the project and as part of the Empire Building Challenge was to be carbon neutral by 2035. So we said that is the end date, right? And what do we need to do up until that date to make that happen? How do we reach that goal? And that's going to happen over time. And that's when we start thinking about financial pieces, social pieces of that, all those different challenges, and thinking about how do the tenants move in the space? What is the stacking plan? How do we figure things out kind of holistically over time? And so you can see in the bottom of that timeline, there are a few things that there are long arrows for, and that's because anytime you have an opportunity to get into the tenant space, you need to take action and immediately kind of make that measure happen. So any kind of domestic hot water heaters, new radiators in the perimeter, and then the envelope changes you'd have to have, you maximize the opportunities you have available, right? So you really want to make the most of any chances. And then in the short term, we're thinking, okay, well, what do we actually have the ability to touch more readily available? So there's a lobby renovation that was potentially going to be happening, and there's other tenant spaces that are going to be available. So any kind of construction issues or kind of challenges associated with ground source heat pumps, there's already going to be a lot of construction happening at the building. So why don't we take advantage of that and say, what's another layer of disruption if there's already going to be disruption? The tenants won't notice a lobby renovation versus ground source, maybe, right? And let's take it's another opportunity that we can kind of leverage to be able to say, let's do the ground source first before we do some of the other electrification steps. And again, we'll get into that ground source piece. That'll be the focus of the last bit of slides. But in the carbon neutral roadmap, that's basically, what are the Carfax, right? Show me the Carfax, that's what I like to say. Hey, what is the actual results? You're doing all of this work, and what are you getting at the end of the day? What is your actual EUI? What are your emissions reductions? And so, the proposed measures, all the short-term things, all the infrastructure improvements, it's not a major difference, right? We're not here to try to paint a prettier picture than it is. Our models are not suggesting that we're gonna get more savings than we're actually going to get. It's only an 8% reduction in energy or in emissions in that steam pie. So that's a key piece and key thing to understand, right? That it's be able to actually reduce steam. It's not going to happen overnight. There's a lot of infrastructure changes that have to happen and large investments that have to be made by buildings to be able to get to that point of carbon neutrality by 2035. And once you do complete that entire roadmap at the very end, you do see that 50% emissions reduction, right? You do see a lot of change that's happened, and it's really substantial. But at the same time, there's a lot of capital investment and a lot of work that's happened to get to that point. And one last piece too, that emissions in 2050 or 2035 rather, a good piece of that is electricity emissions, and that would go away with decarbonization of the grid, but we weren't accounting for that as part of this graph. So that 49% would become something much closer to like 80% or so, or 90% even. And you do see the gas there, but that's for cooking gas for tenants, which is not part of the study. And then just to get into the ground source heat pump piece, so this is kind of the innovative solutions and strategies we're looking at as part of this study. Ground source heat pumps overall, Jeff will get into this I think a little bit more later, but ground source heat pumps, we're trying to reject heat into the ground and then pull heat from the ground into the building, depending on what the building's needs are, right? So thinking of it as the thermal battery again, being able to leverage that heat when you have it available. These are some of the MEP systems that we think of when it comes to ground source heat pumps. You have the manifolds, you have potentially heat exchangers, you have potentially 6-pipe heat pumps. It's a little bit different than a residential application as we're trying to be able to inject that heat into the hot water loop or reject that heat from the chilled water loop into the ground. And then as far as the innovative technology goes, so there's a few different things that you may have seen that's kind of become much more burgeoning in the New York market, a few different things that are from different vendors. So on the left side here, I want to highlight Celsius. So this is a new technology that's been kind of implemented and taken from Europe and moved over to the US now. And so there's a pyramidal directional borehole technology. So the pyramid, think of it as that drill right there at the top of the, that shown in the picture right there, that's the top of the pyramid. And then the boreholes would fan out at an angle, kind of hitting those 4 different faces of the pyramid. So you're able to, meet as much basically heating capacity as possible with a very small area that you're addressing or kind of have access to. So it's really able to maximize the heating capacity with a very small amount of area. So again, helpful for dense urban environments. And then on the right side, from another company, Urban Geo, again, based out of Europe, but used by Brightcore here in the US, is a custom mini drill rig. So this mini drill is able to get into basements of buildings and actually drill boreholes. And so this is about 10 feet tall when the boom is fully extended, and we saw it in action in the Upper West Side in a project that was already been drilled, and pretty interesting technology. And this made a better application and fit at 520 as we were looking at different basement spaces we had available to do drilling. And so you can see kind of an overview of what that looked like at the building. This is a floor plan. So on the left side of the drawing, the northwest side of the building, it's actually an alleyway, so you would be able to roll up a traditional drill rig, like kind of a truck, and do any drilling you would need there. But on the south side of the building and on the east side of the building, you have some available space. And this is, again, from a tenant turnover that happens. So you're able to see, okay, well, we have now an opportunity to make use of that space for something a little bit different for a period of time. And so we're able to find a way to get the mini drill rig into those spaces and then be able to drill a whole bunch of boreholes. You might be looking at this and saying, okay, well, that's not much area at all. That's really kind of just a fraction of the total building's footprint. But again, with this directional drilling technology, we're able to unlock almost 60 to 70% of the building's, the amount of ground below the building, and use that as the thermal battery. So even though we're only able to get into a few spaces just because of the tenant constraints and all the existing requirements in the building, we're able to unlock most of that ground heat capacity. And overall, that led to about 300 tons of capacity, which is pretty substantial when thinking of what a traditional New York City high-rise might be able to previously unlock. And so that heating capacity was actually going to be able to address about 75% or so of the annual heating loads of the lower half of the building, which again is a pretty substantial part of that decarbonization puzzle here at the building. So you can't really see it very well, but this is our concept layout. So you can see how we're actually taking over that south side of the building, and that storage room is now becoming a new kind of plant room for the heat pump system. So we're installing the manifolds, the heat pumps, the pump sets, the heat exchangers, panel boards, everything else, right, is going to be taking over that new space. So we actually still do need space for the equipment. It doesn't just kind of sit below the ground. You do need that MEP space in the actual building. But we're able to find that space for it and move that concept now to a DD set. So this is our DD layout. So just to kind of show you again at a high level, and really excited to continue working with the building and iterating on this design to figure out a way to kind of move it forward down the road as we're kind of like implementing this actual project. So it's very exciting to be working with Tishman Speyer and their team, and definitely hats off to them for being innovative and considering this as a strategy. Some brief takeaways here. That really the high-rise decarbonization, there's no silver bullet. There's not a one-size-fits-all solution. You really need to think about what's happening in the building holistically and all those different pieces, but it is achievable. And so you can't kind of just say, okay, high-rise, we have to like move on and kind of address other buildings. High-rise is possible, it's doable. We should be considering it today and thinking of ways to make that happen for all sorts of different high-rise buildings across the city. But it's really not it doesn't happen overnight. That flow diagram doesn't become filled with equipment overnight. We need to think about that whole process over time and start planning for it now. We need to think about reducing the heating loads, recovering the heat, and then electrifying to be able to make sure that that's happening in a very efficient and effective way so that we're not throwing heat pumps and all those problems at the solution immediately. And then other pieces here, upfront buy-in across all teams is critical. Didn't mention this too much, but it's not just a sustainability team. If you're a sustainability consultant that you're working with, you need to be thinking about the engineering staff, the chief engineer at the building, the operations teams, thinking about also the leasing team, right? Leasing was something that, again, can be a challenge, but it's something that you do need to consider and is a real kind of part of this stakeholder that you need to be addressing and considering when you're thinking about these solutions. And then also asset management too. It's not typically kind of a client that we're working directly with in existing buildings, at least from my experience, but they really do have a lot of say and know what's happening with the building in terms of future plans. So when you're thinking of your own future planning, you need to make sure it's aligning with the future plans of the actual building asset management team. And that's kind of that holistic planning piece, right? So thinking about equipment useful lifetime, occupant schedules, when are people moving in and out? What are those planned projects like the lobby renovation that I mentioned? How are these all going to tie together so that you can make your decarbonization kind of work within the things that are already existing for the building? But making sure that you're also addressing all the stakeholders' needs, because those needs, right, they're your client, so you need to make sure that you're addressing their needs in that process. And then also lastly, right, there's new innovations in technology, like the drilling ones that I mentioned, but also heat pumps too. There's a lot of exciting things happening with new refrigerants, really high temperatures being able to be met, potentially even steam in some cases. There's some constraints available like with all those right now, but keeping aware of what's happening in the new technology space allows you to kind of take more creative solutions and think about the problems a little bit differently. So definitely something I'd recommend to be kind of aware of. So yeah, these are the key takeaways. We do have the PDH questions. Scott, do you want to go through those? Yeah.
Thank you very much.
Yeah, no problem.
Really appreciate it. Pass the mics around. Does anyone from the audience have a question? Yes.
Yeah, well, I don't know if you know this offhand, but what was the total cost for the geo plan at 520?
So I'll just repeat the question. What is the total cost for the geothermal plant?
I'm not at liberty to give that information out. We actually have a lot of different iterations too, so we can talk more about what the range is, but the range is, depending on the iteration and what's actually happening, is somewhere between, we're seeing like 8 million up to 15 million, and that would depend on a lot of different factors in there.
What was the capacity for the 15 million?
Again, a range of like 100 to 300 tons, depending on the iteration.
The pyramid, does that have to stay within the footprint of the building?
What was that, sorry? The fan?
The pyramid drilling, when it fans
the-
outward, does it have to stay within the footprint?
I think that's outside the building, yeah.
It's allowed to go outside the footprint?
I think it has to, I think it's still be in the property line, but outside the footprint. So the pyramid
So
fan.
the property line, okay.
That's like that one specific technology and vendor. I believe that, you'd have to kind of confirm with them, but I believe that's outside the building. It's not intended for in-building use because the drill that they're using is about, I think it's a typical kind of boom. The custom drill rig is able to still do directional, but it's not, you still need like one borehole per every well.
Okay,
Instead of the pyramidal is kind of like all coming from that one like small footprint that you saw in that picture.
on the outside, okay, thank
Yeah,
you.
no problem.
So one question I don't know if I understand correctly, but 2035, you want to achieve the limit that local law 97 is going to be?
No, so I should have mentioned that actually. The building in that 2019 year, right, where it's already very efficient, it's actually pretty much meeting local law 97 limits through every compliance period. Up until about 2040, I think, depending on the decarbonization of the grid, but 2035 wasn't a concern really at the time, so we're actually not able to take any emissions reductions credits as a kind of financial consideration, but it was to be fully carbon neutral by 2035 was the goal.
Yeah, what's the depth of each of those boreholes, and are you able to get like different depths with each of those, like the pyramid one versus the custom rig?
I'm not, again, not a geo expert. I'm gonna put my geo attempt hat on here, but so at least at this project, we weren't looking at the pyramidal one, so we're looking just at that custom mini drill rig, but that's able to go down to about 500 feet, and then the ones we were doing on the exterior of the building up to 1,000. There was legislation that was passed allowing you to drill beyond the 500 feet. Was it 500 feet, 600 feet? I can't remember. Yeah, it was down to 1,000, just because I think deeper, at least from the consultant we were working with, any concerns around potentially like not really knowing where you're drilling as easily and other kind of constraints and challenges associated with that. And we were right on the property line, so we didn't really want to have any issues with that because we've heard of other problems in the past where you have to backfill and things of that nature, which really wanted to avoid, so.
I actually have a question. Hopefully Jeff, Griffin, and Richard, you can take a turn on this. So we're moving into the future. We're moving into a warmer future. We're moving into a future where more buildings are going to be using geothermal. Is there any future concern about the capacity that's going to come out of that existing borehole that you're drilling in 2024, 2025, in 2040, or in let's say 2035, when you're looking to make your clients' goals of 50% reduction? Griffin, you want to hit that first?
I'm not sure, to be honest. So from what I do know, I'll say I don't know like the historical trends over time of like how, if we look at like 1 degree Fahrenheit, 2 degree Fahrenheit, wherever we're at right now locally, how that's changed the ground temperature and how there have been like larger trends over time associated with climate change. But what I do know is that like definitely on an annual basis, right, you're seeing very big changes in ground temperature when it comes to using geothermal. So I'm not sure how much the weather contributes to that, but in general, if it came to heating, warmer ground would be a better thing, but it would just make cooling a lot harder. So you really want balance when it comes to geothermal. So if there starts being imbalance compared to your original design, I do imagine there would be some challenges, I guess.
Richard, since you seem to deal with heat pumps every day of your every day.
Every day and every hour, it seems like. I agree with Griffin. It's about balance and really just understanding the building's operation to ensure that you're not overheating, overcooling the earth, maintaining that balance and truly understanding the energy that you're putting in and the energy that you're taking out.
And Jeff?
I think these two gentlemen answered that pretty well, but yeah, what we're doing as a company is we're developing a lot of fiber optics down the hole. We started that at Epic Corporation in Madison, I would say 15 years ago. and we really trend the formation temperatures every 50 feet from top to bottom. And that gives us a good annual sense of what's actually happening throughout the formation. And then you can also identify what formations are actually your high performing. So you might have a formation section that actually does not store energy, but you might have a deeper part of your formation actually will store the energy. So you can kind of really understand what's going on, and that helps you with your long-term projections of the performance of the ground and the water temperatures that it will provide to the heat pump. Yeah, like they were mentioning, you just got to really monitor it and making sure you're getting back to some type of balance point to make sure you have enough storage for the next year.
So you're saying that you're not monitoring just water in out of the hole, water back from the hole, you're monitoring the entire hole?
Yeah, I would say almost, I don't know, over 50% of our projects today, we're putting in multiple just water wells, and we drop in fiber optics. And then we get real time back from multiple locations throughout a ground heat exchanger. And our latest one is Princeton. I believe they put in 6 monitoring wells. And what they were really interested in is, does the energy actually leave your site? Okay, so they put 3 monitoring wells on the perimeter of the ground heat exchanger, and then we got some in the high density sections of the field. So you can kind of see, are you really building up energy or not? Or is it leaving your site or not? So we're getting more sophisticated with how we're monitoring our formations.
You don't suspect that there will be a problem with that heat pushing to the next property line?
Well, that's what you hear a lot of theory and worries from communities. It's been, on people's minds that you're putting all this energy in the ground, it's leaving and it's warming up the local water well, right?
And ground.
In the ground. And what we've been proving over time with all our monitoring is we are not actually changing your water temperatures. So it's very interesting. We have a case down in Tennessee. The job's being built right now. It's a very large project. And the city and the state are making us put the water wells in because they want us to monitor their local water well to make sure we're not actually changing the temperature for the city.
Of course,
Yeah.
of course. Thank you.
I have a question from the streaming audience that's also about this terra incognita below the buildings that we're drilling into. And they ask, where do you find out what is below the building? Like waters, subway tunnels, other infrastructure, which that's in the layer close to the bottom of the building. But there may be other things that are deeper. Where does the building find out about that?
Again, in the court of the geothermal consultant, I'll put my best effort here, but from what I understand, those subway tunnel maps are actually pretty well defined, and so those are published over time, and maybe some people have access, some people don't. I'm not sure if it's fully public, but people know if you're kind of tasked to do that, and you always submit any project to the DOB, they would also tell you there's the subway right there, you need additional permits if you're going to do drilling near any MTA subway tunnels. So that would be kind of clearly well defined. And then below the building itself, really there shouldn't be, in theory, any surfaces besides like your structural piles and things of that nature. So, it's just whether it's bedrock or soil or other things of that nature, but you really should be doing a test well anyways. And that test well would help you really, at least for that area and that region of the building and that footprint, to be able to define like what the actual composition of the earth is below the building.
In my experience, it's been the drilling outfit is a separate trade and subcontracted to the project. And then depending on that outfit, they will be more or less transparent, especially if asked or not, for this information, because they wind up being liable unless the contract that they're subcontracted to specifies otherwise. So it's kind of a complete package when you get the drilling, but when you're making the planning and the project plan, that's something that you have to make sure to integrate.
Yeah, I mean, as a designer, we definitely want to make sure that we have that data because then you can actually say, okay, well, what is the actual size of our equipment? What can we actually expect in terms of our heating and cooling loads? If you don't have that test well, then you're kind of playing with fire a little bit because you don't really know what exactly the thermal conductivity is going to be and other things of that nature in terms of that test well.
Great. Just a couple of notes. We will be showing a PDH scan again, so we just fill out one for the entire panel, and we'll be showing that right after the next presentation. Note 2, Kelly Westby. Kelly, can you stand? Where's Kelly? Kelly is in the back. Kelly is going to be chairing a student huddle for the students in the class. Hopefully, Kirsten can join that. There's a lot of money and opportunity for students through ASHRAE, the shaking of the head, right? So there's actually money, and there's challenges set up. So please find Kelly and Kirsten when we break for lunch and huddle with her and see if there is some advantage and great benefit working with them. Thank you for all the students who came. One more just to assure you that all the presentations in these sessions, the videos, will be within 2 weeks sent to all the attendees. And within that, we're asking a lot of questions, and we have the answers, and we're documenting them. We're going to be providing, let's call it a Q&A package of those questions and answers, so you'll have that as a resource as you go forward on these diverse topics. Without further ado, I'd like to introduce Sarah McLean from WB Engineering. Her focus is in EV infrastructure, and let's welcome her to the stage. That's all you need to know.
All right, thank you guys for having me today. The learning objectives we're going to go through for my presentation are going to be going through the recent codes regarding EV infrastructure, a couple, high-level EV project type points and challenges to considerations, and infrastructure deployment timelines. So for New York City, the current codes and standards that are applicable to EV are as follows, and we are going to dive into those right now. So Local Law 97, everybody in the room very familiar. There's nothing within Local Law 97 that requires EV infrastructure, but if you are installing EV into your building property, you are going to have to report on that for your Local Law 97 compliance. The electricity that's used for the EV supply equipment can be deducted from your overall building use, but there's some requirements for that deduction to be met. That equipment is going to have to either be separately metered, or your EV infrastructure equipment will have to have integral metering that can report out to meet those deductions. New York City Local Law 130 and Introduction 694 is really the main local law right now that is driving requirements of EV infrastructure in the city. So if you are doing alterations of your parking garages or your lots that require an increase to your electrical service, you're going to need to provide EV infrastructure for your project. Excuse me. So for parking garages, what this means is that you're going to need to provide a minimum of 3.1 kilowatt chargers to 20% of your parking spaces within your garage. You need to at least provide provisions for that. It does not need to be installed day one for the project, but having the capability to install that as you go along. And that's going to be increased to 40% of the parking by 2030 under Introduction 694. So a 3.1 kilowatt charger, that's a level 1 trickle charger, pretty low power requirements there. And for open parking lots, if you have open parking lots within your facility, you're going to need to provide 11.5 kVA to 20% of your parking spaces from your electrical supply panel. Similar, at a minimum, you need to be able to provide the raceways and the breakers to provide this electrical vehicle charging equipment. So those 11.5 kVA chargers, those are like your level 2 chargers. Under the New York City Building Code, there's nothing in the code right now that says you need to put EV charging equipment here, here, or here. But if you do put it in your project, you have to meet the accessibility requirements. That's 5% of your EV charging stalls will need to be provided for ADA accessibility per type. So if you have On your site, you're planning for level 2 and level 3 chargers. At a minimum, you need one per type of charger, with that overall minimum being 5%. Those spaces need to meet van-accessible parking requirements. So these spaces are much larger than your standard stalls between 8 and 9 feet. The van spaces are typically between 11 and 12 feet with access aisles of 5 feet wide. The equipment also needs to be located along an accessible route, and the controls need to be able to meet accessibility requirements. Under the New York City Energy Code, right now, the only requirements fall under the residential sections of the code for 1 or 2 family dwellings and townhouses with building on site. You're going to need to provide 140 amp outlet per unit, or at a minimum, that spare capacity and conduit to achieve that. And then residential occupancies with common parking areas, again, a 40 amp outlet or spare panel capacity for 5% of that total common parking. Just real quick, quick diagram of kind of an open lot configuration where we have our EV charging equipment. Somebody told me there's a pointer, let's see. EV charging equipment, and here's your large van stall with your access aisle, with your charging equipment within that access space, and then path of travel to whatever this facility is. Some considerations for project types. What kind of project are you considering for your property, right? There's a lot of things that come into play when planning for these projects. Are we looking at a public access site? Are you looking at a private access site? What sort of chargers are you going to put in, and what's the use case for those chargers? Are you looking to serve your tenants? Are you looking to serve the public? Are you looking to serve some sort of fleet vehicles that you might have for your facility? That all comes into play when making the decisions on what kind of project type that you're going to be considering for EV infrastructure. So like I said, those level 1 chargers, those are smaller trickle chargers that produce 1 to 2 kilowatts of power. You're really not getting a lot there. Those are kind of more for at-home use or very backup scenarios. Really, when we're talking about these projects, we're talking about level 2 and level 3 chargers. Level 2 chargers, you're going to get 3 to 19 kilowatts for each unit, depending on what you need. And those are getting you a full charge within 6 to 8 hours. Then level 3, those are your DC fast chargers. So these are big power units. Right now, some of the largest ones that we're seeing are 400 to 500 kilowatts per unit. That's a lot of power, depending on what your use case is. So understanding your use case, right? Are you expecting the demand to kind of be all at once? You have all of these vehicles possibly charging at the same time because they're charging during business hours. Is this a destination site where you're trying to get revenue for your project with the DC fast chargers? What is the demand on those high power units that you need to consider? Is it a fleet charging application, right? Are we charging our vehicles overnight when you can kind of stagger when the vehicles are charging? So there's a lot of things to take into consideration when looking at what the project needs are. All right, so some impacts to these projects. The project location. Is this a brand new development? Obviously, it's easier to make the accommodations for a brand new project. You can do all the planning you want up front. You don't have to worry about some specific challenges that come with retrofitting these systems into your existing facilities, but that's not always the case, especially in New York City. Not a whole lot of spare land to be working with. Are we dealing with an existing lot, or are we dealing with an existing parking garage? There's different considerations that you need to take for each of those circumstances. If we're an existing lot, where are we getting the power from? How are we routing it to where you want to be? There might be a lot of different entities at play kind of dictating where that charging site on your property is going to be. Same thing within parking garages. Where are you trying to locate these? Safety concerns you have to take into play. Is there going to be easy access to those chargers if, forbid, something does happen where the fire department needs to come into play? And how are we getting power to that location, again, if it's on the very top or very bottom of a large parking garage structure? What's your power source? Are we running from existing infrastructure? Do we require a service upgrade, or are we looking at new services? It really depends, again, going back to that use case and charger type, on what the powering solution is going to be. So it really is project dependent, and working with the end goal for your project to see maybe there is enough power on the existing system to power your level 2 chargers. If you're trying to put in a significant amount of level 3 chargers, depending on your current service or utility requirements, you might require a new service. Real estate considerations. These units come with a lot of things that you need to consider. There's power cabinets for the larger units, new switchgear, battery cabinets if you're doing microgrid solutions, generators if this is a critical install that you need to make sure those units are staying up all the time if you're doing like a fleet EV charging. If your fleet can't charge, that's not good. And then if you're accommodating any canopy or solar design, all of these things take space. So you're gonna need to accommodate for that in your design plans as well. And outside of New York City, utility transformer space as well. Most of our transformers in the city are in underground vaults. Site limitations you need to think about. You know, like I said, you might have an idea in your mind where you want these chargers to go, but there's a lot of things that come into play when finding the correct location for them to be. You know, we need to take in building property setbacks in mind. We need to take into consideration the ADA accessibility. If we're on a parking lot, we need to worry about, you know, does the grading meet the accessibility requirements for those stalls and path of travel and access aisles? If we're putting in new equipment, you know, there's a lot of concrete pads that kind of go in to support a lot of this equipment. Are we now going into territory where we have to consider stormwater management because of impervious areas? Just a couple examples of some charging around the city. This is the Gravity Charging Center. This is a new charging infrastructure project where they installed 500 kilowatt chargers in a parking garage. Here's just kind of your standard in-garage Tesla supercharger installation. These ones are the curbside charging that are provided by New York City. There's about 100 of these right now distributed throughout the city. One of the challenges that I've heard about these is people just park there, right? So if you have an EV and you're looking for this curbside parking, there could just be a standard vehicle parking in that location because we all know how hard it is to find street parking in the city. And then here's an application for ChargePoint where they are in an above-ground parking lot. So there's a lot of different applications throughout the city where charging is installed. This map up here, this is from PlugShare. These are all the EV charging locations within Manhattan and Queens. Couldn't quite get Staten Island on the map. But there's a lot currently in the city right now, and that's going to keep growing. I'm going to go through this slide real quick. This is more for outside of New York City, throughout New York State. You know, you really need to consider your permitting for these projects. If it's a small level 2 project, permitting is probably going to be pretty quick and easy. But if you're looking at a larger scale EV charging project with these DC fast chargers, say you're installing a private fleet lot or even a public accessible DC fast charging lot, there's a lot of things that you need to consider going into permitting, and permitting can take a very long time. So really optimizing your engineering process is key, and finding those design professionals that are proficient within the EV space to help you from the idea of this project to the very end. I can't stress enough, spending time on the feasibility and the due diligence for the project is going to pay off in the long run before you even get to engineering, because there's a lot of things that you need to consider upfront in these projects for a successful project to go through. Or an early utility engagement. Engaging with the utilities early. In New York City, we're dealing with Con Ed. The process can be slow, so you need to really take into consideration the timelines associated with that. And then just once you kind of get through all of that, your standard engineering design and permit documents, I kind of joke usually that the actual document development itself is the easiest part of the project, right? It's all the upfront stuff and dealing with the utilities and the permitting. That really takes a lot of time out of these projects. Just some design considerations. I don't know why this looks like a Nintendo resolution, but we're gonna roll with it. You know, setback impacts, where are you putting your equipment? Where are you putting your chargers? Where are you putting your support equipment, your power cabinets, your utility transformers? What is the infrastructure layout and utility points of connection? Do you have landscaping on your site that you need to consider? We've run into that a lot with, you know, where we're locating our equipment. Are we impacting trees? What are the different dispensers? How are you getting into the lot? What is the access and queuing? And then what kind of chargers, what kind of vehicles are you looking to serve? Are you looking to serve your standard passenger vehicles, medium, heavy-duty vehicles, buses, fleet vans? Really kind of taking all of those factors into consideration when you're looking at these projects. And then, like I said, understanding your infrastructure timeline is huge, huge, huge. You need to be flexible with these projects. You're going to go in thinking, this is going to take me time X. No, it's not. It's going to take you time Y plus time Z. The utility coordinations and final designs, it can be painful. There's a lot of back and forth with the utilities that are required if you need service upgrades and new services. Utility transformers and metering equipment. It's brutal out there, and it's not getting any better. We're looking across the country at a standard 9 to 12 months minimum for new utility transformers for these projects. If you need new easements that need execution and recording, that's processing with legal departments and recording entities. HJ permits and reviews, these can be very lengthy depending on the project type, and electrical equipment procurement in general, not just the utility transformers, but if we're looking at large switchgear equipment to power some of these larger DC fast charging sites, some of that equipment is also out 1 year plus. So just be proactive, engage your design professionals early. The type of project and the type of site that you are considering for EV installation is going to really play a factor in what the project entails. The project timelines, understanding those and having contingencies for those are imperative. Zoning regulations can be brutal, depending on where you're trying to permit these projects. And somebody else said it earlier today, educate yourself, right? Educate yourself on these systems, educate yourself on these requirements, educate yourself on what's going on right now with EV infrastructure as a whole. And then just kind of have patience, right? And work with your design team, be flexible, be ready to kind of pivot when needed. That's it. Right.
Thank you, Sarah. Audience questions? Well, I have a couple of questions. It just seemed, yes.
I'll just repeat that for the stream if you don't mind. So code requirements, are those for parking lots? Are those retroactive to old ones or and existing ones, or are those only for new ones going forward?
Yes, those are retroactive as well. So if you have an existing parking lot or an existing parking garage and you are doing work on your site that is driving a upgrade of your existing electrical service, that's going to trigger now you providing provisions within those existing lots and garages.
Yes.
When it comes to the actual charger for the cars, has the industry solidified a standard? I know there's been a couple of different charging port types, and certain companies have come out with adapters, but I believe Tesla's version is becoming the standard. Is that accurate?
Correct. So the industry is working towards adopting that NACS, North American Charging Standard that Tesla uses right now. But like you said, a lot of the vehicles, you can get adapters and things like that. And what we're seeing for a lot of the current installations, especially because some of the funding tied towards these products requires specific adapters as well, is dual ports. So in the past, you could have one DC fast charger that has 2 cables to serve 2 vehicles simultaneously. What we're seeing a lot of the installers doing now is instead of having the same port type to serve 2 vehicles, you have 2 different ports now, so you can use either or to serve your vehicle needs.
I'll just ask the panelists then, if you would repeat the question once they hear it, because maybe not everyone in the room heard it, but also the streaming audience and the recording. So please, if you wouldn't mind, repeat your understanding of the question, summarize if you need to, and then answer, please.
I saw 2 interesting points in your presentation, and they go back to, one of them goes back to Griffin's presentation, is you need to make decisions based on limitations as well. And you simply may not have the electric power to do the local law 97 upgrades at 520 Madison right up front. There's a development of that electric grid. Is EV being pushed aside at times in buildings because it uses power that maybe the building wants for efficiency upgrades?
I think it's still so new in adoptability that it might not be on the forefront because there's nothing requiring it right now. A lot of, if people are looking at it as an amenity, right? It's a nice to have. If we can't have it, Nobody's telling me I need to have it. But if, New York State, they've passed a law where, after 2035, you cannot sell gas vehicles. So that's going to drive adoption within New York State and New York City. So property owners are going to have to think about that adoption and the people that are going to be using their facilities and, thinking about these things now. And when you're looking at building electrification as a whole, you should start thinking about that as a factor early on as well, so that you're measuring twice and cutting once if you do have to do some sort of infrastructure upgrades.
Absolutely. Yeah, that's really kind of what the concern would be. It just seems in the outdoor EV infrastructure, I didn't see any solar panels hanging over the equipment, right? Why not shade the transformers and the stations with solar panels, and now you're adding towards the cost?
Cost and permitting, that's
but-
where we're seeing the challenges
Right.
with that, yes.
That's both
But-
cost and electric use.
Yeah, and a lot of people are started to gravitate towards that canopy and solar storage use because it is, a big complaint within the industry. Like, you're providing no protection over these people trying to charge their vehicles, while you could provide that protection with the benefits of solar storage and battery-powered systems as well.
Right, I mean, I'm always putting in one of those window shields in my front window in the summer because it gets so hot, and it would just be great while I'm charging up my vehicle to have some shade.
Absolutely.
And then if you knew there was solar panels on top of it, it just kind of,
And a lot of work with microgrids to try to help with that peak shaving, depending on where you are, for helping with the demand charges on the back end.
Is there any coordination between the geothermal field and these parking garages? It just seems you have this dead space, even if a car is on top of it, there's not much going on. When I walk by a geothermal well on the sidewalk, it looks pretty. It's kind of like that hatch, a little different, but it's not doing anything, right? We don't see that because the vault is underneath. But it just seems like it would be such a good place, parking garages and basements and outdoors, to have that field. Is that being discussed?
Yeah, all our new projects are under buildings.
Under buildings, but are they
Yeah, under
specifically
parking
looking at
garages, parking lots, under the footprint of buildings.
So there's no code issues,
There's no
no
codes.
problems,
Well-
safety?
There's a couple states we're fighting with right now where they do not want to allow geothermal heat exchangers below their buildings.
Okay,
Yeah, there's a few states out there that we're trying to get that changed.
okay, great.
I have a related question that maybe actually might tie these things together, which is about the demand for level 2 and 3 charges. If that exceeds or pressures the overall capacity at the site, is that a use case that people are invoking as a battery storage use case so that they can slowly charge and spread that demand over, say, the entire day, charging the battery, and then put out a big output while being tapped for charging?
Yeah, no, definitely. Like, microgrids are one of the bigger solutions that we consider for these projects, but it goes back to that use case, right? When do you need that charging? How many cars do you need that charging? If you're trying to charge a fleet of 50, right, at the same time, that battery's not going to do too much for all of those cars, right? So it's about balance with the systems and really understanding how those systems can supplement your use case and your power needs.
Great, thank you very much, Sarah, really appreciate it. So the next of our panel discussions is Randy Topp. Randy is the Senior Vice President of Energy Services and National Operations of Support for Ainsworth. Let's welcome Randy to the stage.
All right, perfect. So just some learning objectives. There's lots of aspects to the energy efficiency path, as you're aware and talked about this morning. It's going to take a lot of collaboration between different parties in regards to getting the initiatives for the end goals to the clients. And I want to just touch on some really innovative efficiency measures that some others will talk to as well. So it takes a lot of providers. It takes energy services in terms of audits and studies and carbon reduction planning committees and engineering and suppliers and implementation and the contracting, commissioning, testing, measurement and verification and financing and so on to meet the efficiency and carbon reduction goals. I want to touch on sort of two case studies or some case studies. St. John's University, which is the portion we're doing in regards to as a contractor on the building side for a geothermal loop. 345 Hudson, which has done some amazing innovative measures that we're involved with that through Hines. The Omni Berkshire Hotel and Lighthouse Guild are both design and energy efficiency studies for compliance with Local Law 97. So in the Omni Berkshire Hotel, it's a midtown hotel, 399 guest rooms and suites, 19-floor building, total area 230,000 square feet, kind of 1920 vintage. They were looking for a cost-effective strategy to modify their systems in terms of their mechanical, electrical, plumbing systems to reduce their consumption and so on, while maintaining occupant comfort, obviously critical in a hotel environment, and also looking for compliance with Local Law 97. The audit is being done through a joint effort of consulting engineers and their chosen contractor. So this slide here, just want to touch on it. Under the 2024 to 2029 sector, the emissions right now are 1,494 tons of CO2 right now as a baseline, and whereas the limit for this type of building is 2,300 roughly. So right now they're 35% under. So they're already in compliance. Nevertheless, they want to take a proactive approach in regards to seeing what else they need to do. As you move along to the right-hand side, though, if you electrify the grid, it drops down, but so does the limits, and so therefore you're going to have these different fines as they move along. So what we proposed to the Omni Berkshire Hotel is 18 standard kind of energy conservation measures, if you will, variable speed drives and fans and pumps. Lots of building automation, control optimization, kind of low cost, relatively easy to implement, generally a good return on investment, has a payback, if you will. Whereas you've got sort of 9 capital intensive measures where you want to do quarter makeup air and condenser water heat recovery, water source heat pumps for domestic hot water heating, converting one of the chillers to a heat pump, those kinds of things. They're good at reducing your greenhouse gas emissions and your carbon footprint. But it's not great in terms of it actually a return on investment. And these ones obviously take a lot of engineering and planning to execute. Right now, this study is nearing completion. It's about to be handed in actually in the next couple of days, with cost savings, return on investment, and so forth. So then what we show out of all of this then is if you just do the initial things like the retro-commissioning measures, you get a reduction in your carbon footprint. If you do some of the energy conservation measures, that again, those ones that are fairly relatively easy to do, it moves it down to 1,147 tons of carbon. Then if you get the greening of the grid, which is probably going to be more like towards the 2035, gets you down even further. Then if you do the capital improvement measures, how does that get you down to 366? And then eventually you're going to have to buy renewable energy credits to get you to a lower level. We just chose 20%, but you would need more to get it to net zero. So moving to the Omni Berkshire to a different location, the Lighthouse Guild, which is a 7-story, 160,000 square foot mixed space facility, daycare, clinical space, offices, and so on, below-grade parking. Again, kind of a similar study that we conducted. They wanted to, again, a cost-effective strategy in regards to mechanical, electrical, plumbing systems, and so on to reduce their consumption and conformance to Local Law 97. Again, we worked with a consulting engineer and a local contractor to get to the end goal. Similar thing that I showed in the Omni Berkshire Hotel is that right now they're at their baseline right now, just under the threshold limit. So there's no penalty to them right now until 2030. But in 2030, they will be over even when you do the greening of the grid. And so they're going to have to take some measures soon to start to move towards reducing the carbon footprint. Otherwise, they're going to be in a big penalty position. So similar to the Omni Berkshire, again, there's energy conservation measures, kind of the standard fare stuff. In this case, it's a lot of retro-commissioning that is needed here to get them down. There's some pump optimization. Again, fairly low cost, relatively easy to implement, good return on investment. And then there's 5 capital intensive measures. Again, it's changing out the building automation system to get to more analytics and so forth. Air source heat pumps for domestic hot water heating and so forth. Again, measures at reducing the greenhouse gas emissions with, less of a return on investment. So similar thing, you know, where here they are, if you do the retro commissioning first, what it gets you down to, then the energy conservation measures down to 1,096, taking factoring the greening of the grid, the capital improvement measures, then if you need to buy carbon credits, you know, how you can move your footprint down as you go along. It's kind of more of a stepped approach, but probably a way to go in terms of limited capital funds. So those are the kind of the two studies we did, again, Omni Berkshire Hotel and Lighthouse Guild. Now I want to just speak to where we've done some implementation of actual measures with different partners. And so the contractor's project value on this one in terms of the mechanical systems was $9 million, including controls, but that did not include the geothermal field portion. Still under construction right now. This is in Queens. Summer of 2024 is the completion. And so it's a new health sciences building, 3-story building. It's got classroom, teaching, scientific rooms, and so forth, fume hoods. The building is one of the first, well, is the first one on campus not to utilize the central steam plant for heating and cooling. It's really an all 100% electric building and is scheduled to have solar PV on the roof. It's not on there yet, but that's to come. It's about a 70,000 square foot building. So we were involved in supplying and installing ground source heat pump chiller modules, 307 tons of cooling, 211 tons of heating. They're basically multi-stack type modular units that allows kind of simultaneous heating and cooling capabilities in terms of being able to heat and cool each module, if you will, and then it feeds chilled beams, which I'll speak to in a second, at any given time. The ground source system field consists of 52 wells, 499 feet deep, which feeds and as the energy sink and source for the heat pump unit. So just want to show this. So which one did you press? This one. So this is the modular heat pump system there, and that's the geothermal wells. We were involved in that, and I'll speak to this in a second. This is the 6-pipe control valves on the chilled beams. So there's primary areas supplied by 2 air handling units up in the penthouse that then feed down to the chilled beams. And the chilled beams are basically a coil that sits in the ceiling space, and the air from the air handling units goes into the unit, and it induces air across the coil. And you provide the heating and cooling effect through the water that's in the coil. And so it's either heating or cooling in terms of the water that's in there. Again, it has that 6-way control valve, which is fairly complicated. But it basically allows you to provide very efficient heating and cooling to where you need it. There's no perimeter heating along the building at all. The air handling units are 16,000 CFM for 42 tons of heating and cooling that come from those units alone. And they've got variable speed drives and on the fans and pumps and so forth to optimize the energy use for almost really any variable load. So that's at St. John's University. And again, just wanted to speak to the portion that's within the building where the piping comes in from the geothermal field and kind of what went on further along with that. So I want to talk about 345 Hudson and 555 Greenwich Ave, and I know that Jeff and I think Richard are going to speak a little bit about this, and so I'm just going to touch on pieces of this. So that portion is on the interior piece is $3.6 million, which covers just 4 floors in terms of utilization of the systems. And basically the project is to upgrade back to base and retrofit of 4 floors in an 18 commercial floors. And it's JB&B and others were involved in the innovative measures on this mechanical project for Hines. And so it's quite amazing what they've done here. So specifically at 345 Hudson, the building was, heated from steam radiators supplied by the New York City District Steam. Basically, we removed all the steam piping and the terminal equipment and installed new piping on just the 4 floors, 3, 7, 13, and 16. Those are the tenanted floors, and connected to a new ambient water loop for low temperature hot water, and I'll speak to what low temperature is in a second. Existing or operable windows on the facade of this building at 345, leaky and old, and brick facade and so forth, and so there's going to be considerable losses through some of those, but there will be some replacement of those in the future. It's going to be, it's next to what is at 555 Greenwich, which is a new building, and I think Jeff will speak to that in regards to it has a geothermal field and so forth, but it's interconnected to 345 Hudson. So the interesting thing about the 345 Hudson site is it's got a German-based multi-pass fin tube radiators rated for 100-degree Fahrenheit supply water temperature with a 20-degree delta T. You know, acting as basically terminal baseboards for convection heat under the windows per floor. And so we're kind of actively watching, you know, how well this is going to work. It's, again, very low-grade heat, if you will, in terms of a water source to replace steam radiators that would be giving out 220 degrees. But you can see, you know, the width of those, of the fin tube there and how wide it is to get that surface area to get the convective heat that you need. It's like 4 times the transfer rate compared to a traditional sort of single-pass type system. 345 included also the energy machine, or they called EM, and you can see them on the picture there on the right-hand side, rated at 52 tons of cooling and 75 tons of heating, which are, again, heat pumps that are providing heating as it relates to the convectors and as well as cooling for air handling units that are going to sit on the tentative floors as they get occupied. The cold side of the heat pump loop is capped at chilled water, and it creates a buffer tank when it's in heating mode for future use on the air handling units that will be installed. And then fresh air supply, again, has to come from a central system, you know, as the tentative spaces are leased out. And I just want to touch then on 555 Greenwich, and then Jeff and I think Richard will touch on this as well, as they've just done some really innovative things by Hines and so on. It has in-floor radiant heating and overhead cooling versus direct overhead air systems in terms of heating, cooling coils and a fan box, really like a chilled beam, if you will. They temper the water and so on. There's no condensate that you have to drain away from these boxes. And it minimizes the outside air, which is what you need to do in terms of conditioning air. Our understanding from Hines is that building is required to drive driving pylons into the foundation. I think Jeff will talk about that. And they put sleeves in terms of where they put the pylons down to rebuild this building to provide that geothermal in terms of the piping loop. And so, as I mentioned earlier, the 555 and the 345, in terms of building addresses, the floor plates will be intermingled and now kind of contiguous. The plan is to have these two buildings and mechanical systems actually operating together.
Great. Thank you, Randy. Audience questions?
And just a reminder to please repeat the audience question before answering.
Excuse me?
Just a reminder to repeat the audience question before
Yes.
answering it. Thank you.
Any questions on those 4 case studies? If not, and you think of a question, we can always answer it after Jeff's or Jean-Simone's presentation. We have 2 presentations left. Why don't we bring up Jeff Erlap from Salsa O'Brien, and let's give him a hand.
Yeah, thanks for having me. I'm also going to invite up my coworker here in a second. Dan will be presenting on some of the projects he is more familiar with than myself. So our learning objectives are really learn some more about the ground heat exchangers, and I'm going to talk about really heat pumps. What we do as a company is when we start out, it could be new or an existing campus, existing building, we get involved and try to help them develop the best roadmap and figure out what are the best technologies to implement, you know, for that building, for that campus, or new building in existing building. A couple things, what we've been really striving for is how do you implement the right technologies and what % of the different technologies should be utilized. Give you a little backstory. I got in the heat pump business back in 2000, and that's all I focused on my whole career. And back then we were just doing little buildings, water air heat pumps, water heat pumps, and we were doing 100% geo. Like when I converted my office building 16 years ago, my office building is 100% geothermal. We didn't have gas in our buildings. Like my building had boilers in it. We removed the gas meter, 100% geothermal. Big difference back then. Drilling costs were a fraction of what they are today. We can't do 100% geothermal today, multiple reasons. A lot of our sites don't have enough land, but even if you do have enough land, the first cost of doing 100% geo, right? The second thing is, how do you figure out what is the right water temperature to design a new building to versus a retrofit? Because that really drives the heat pump technology. What I'm seeing in our industry is too many projects where heat pumps are misapplied, right? They don't understand lift and turn down. So in our industry, we're not getting our engineers educated enough about how do you actually apply the right heat pump to the right application and the right water temperature. You see out there, people are doing a lot of pilot projects, which I quite don't understand why we're still doing pilot projects when we've been doing heat pump projects, right? 30 years ago, started doing heat pump projects, and we're still doing pilot projects because people aren't comfortable enough with heat pumps. So when you look at all these different technologies and how heat pumps are changing, like Griff was saying, is the heat pump technology is, I would say in the last 5 years, manufacturers are putting a lot of money into R&D, and they're developing heat pumps for higher lifts, different refrigerants, and all that to be more utilized in our campus conversions, building conversions, and our new facilities. A couple big things that you're seeing a lot of is ground source, air source, sewage heat recovery, and air side energy recovery in buildings are really your 4 energy sources that we've been dealing a lot with. But then how do you take those energy sources, apply a heat pump, and then implement some type of thermal storage, right? Because it all has to work together, and it all has to be sized properly. When you look at your ground heat exchanger options, right, we have a lot of options today. We have open loops. We have closed loops. We have open bodies of water, like rivers and lakes. You really have to understand what you have available at your site as an energy source. Do you have a retention pond? We use a lot of retention ponds as heat exchangers, right? They might be 4 feet, 6 feet, 8 feet deep. We implement slinky coils underneath a sand layer, and then we have water on top. It's a very good heat rejection device, right? We're trying to get rid of cooling towers, for example, if it's a heating dominant or a cooling dominant. But you can implement also multiple heat exchanger types on one site. We have a large campus here in the US. It's 25,000 tons of heat pump, no gas, but we have 3 energy sources there. We have a lake loop, we have a retention pond, and we got 6,000 vertical heat exchangers. So you got to kind of look at your surroundings and your site and what can we implement as energy sources. Kind of back what I was talking about, fiber optics. This is a project we did, 12 years ago, where this is our first fiber optic project, where we actually measure the ground temperature every 50 feet. And you can kind of see, right, when the traditional sine wave of your ground heat exchanger. I don't have the, but you can kind of see how this project, right, we're actually seeing a temperature change. Sometimes we see ground heat exchangers are so oversized they don't change temperature, right? So what happened there? Your client just paid way too much money for this ground heat exchanger they're not utilizing. It just, right, sitting there. But it's giving your heat pumps optimal water temperatures to operate in. But it's all about that first cost scenario. Griff was talking about, when you look at a building, we really want to reduce the energy first. Once you figure out, reducing that energy, and here's the energy that I actually have to provide, which in energy models, I'm not sure if, when we do energy models, right, they're not accurate enough for us to really hone in on exactly our size of heat pumps. There's always a lot of, extra capacity in our equipment because of our thermal profile developments. But we really strive today to figure out how much simultaneous load can we increase the building to develop for us, so we can really downsize that air source, ground source, right, exhaust air streams to capture all that energy. But this thermal profile drives all our economics for one thing, and it drives our design. So if this thermal profile is wrong, everything's wrong, especially when you get into your heat pumps, and we're starting to oversize heat pumps. Some heat pumps don't have very good turn down. They might only have a 50% swing, and then we have major problems because now that heat pump has to start and stop a lot. So we really must get better at developing thermal profiles and really driving, the accuracy of this, because again, it drives everything. Now I'm going to invite Dan up. Dan's going to talk about a couple of projects. Some have been in operation here in New York City for quite a few years, and some are just in the planning phase.
Thanks, Jeff. So the first project I'll talk about, I'm going to run everybody through a couple of our projects, some various levels of design and implementation. Some of them are already in existence, operating today. This first project here is for L&M developers, where basically a previously vacant lot is now being converted to a pretty impressive development that's going to include no combustion on site. It's going to be net zero upon completion. It's going to have several bore fields, several buildings, and I believe solar panels will be going on the roof. And this is a very long-term project that's supported by NYC to do the initial studies through their Pond 4614 program, and then also working with Con Edison to get some of their financial incentives to implement these types of systems versus a code minimum type of system. This project everyone's probably familiar with, 555 Greenwich. I know a few people had spoken about this already, and I know there's a couple Heinz people here today. So I was intimately involved with this project. I had worked for Endurant Energy, who implemented this project. JBB actually did the MEP engineering on the inside of the building, and then Salas O'Brien did the geothermal design. And this building, I think a couple people had mentioned it, how it's 555 Greenwich it was a new building built right next to 345 Hudson to eventually be integrated together. But 555 itself was a new build from the ground up, and it needed a foundation like any other building. I'm not a structural engineer, but it presented a unique opportunity where they needed a deep pile system to support 555 Greenwich. I think it's 64 piles, varying in diameter from about 2 to 3 feet. And they sit on top of bedrock, which is about 100 to 120 feet below grade. So in each of those 64 piles, actually 63 piles, because we left one pile untouched, where we put fiber optics, kind of like Jeff had mentioned earlier. We put strain gauges, thermocouples every few feet in that control pile, and in some of the piles that had geothermal loops put in them as well. But so we have 63 piles. Each one has an 1.5 inch diameter geothermal loop in it, 3 of them actually, and they're all connected in series. So you have about 360 feet of loop in each of those 63 piles. Currently, I've been inside the building. It's beautiful. I don't know how occupied it is right now, so I don't want to really comment on how much of the energy is coming from the geofoundation, but I know it's doing all the cooling, heating, and hot water. And then I guess as the building starts to fill up, it's going to be a fun project to pay attention to see how much they're actually getting from the geothermal system. let's see, the next project, you may have heard of this one before as well. It's been in operation for a while. This is on Roosevelt Island, Cornell Tech Bloomberg Center. This has 80 closed loops to about 400 feet deep. They were drilled, like most other closed loop systems, but during like a test bore phase, I think JBB had mentioned it earlier here before, we really support doing test bores. This project, when we did a test bore, maybe 9 or 10 years ago, the driller got down about 380 feet, and then they were coming across a lot of water. So they were producing a lot of water when they were drilling, which initially I don't think was expected. So another reason to do a test bore or test well is to figure out, what you're going to hit, both, what kind of rock you're going to hit, but also what kind of water are you going to encounter. So when the driller got down to about 380, 360 maybe, they started getting a lot of water at the surface, which they were able to manage. It wasn't unmanageable, which is good in terms of, keeping the site somewhat clean and making sure you're staying within your permit limitations for discharging to the sewer or discharging to surface water. So discovering all this water made us change the design where instead of grouting those loops in each of those 80 holes, we didn't grout them. It's basically, a void cylinder all the way from grade down to 400 so that it captures that 360 to 400 foot fracture zone where there's basically water from the river, groundwater flowing through. And what that allows us to do is during peak times, if they're cranking the air conditioning in July, and they're really heating up that ground loop in all 80 of those ungrouted boreholes, we could pump off the top 20 to 30 feet of that water table. It's a very shallow water table. So we designed basically a dewatering system like you'd use if you were building a new foundation for a site with really high groundwater where you have to lower the groundwater table in order to build. Same idea. So we pump off that top 20 to 30 feet of water, which introduces fresh water from that deep fissure to replace what you pump off, effectively increasing your capacity during the times where you need it the most. So basically cooling down all 80 of those wells, unlike the hottest days of the year. And it also works in reverse, but this was, I believe, a big cooling dominant project. This project is another one for L&M developers in Brooklyn. I believe we've done a few test bores for this project already. Like Jeff mentioned, a lot of the boreholes we're doing here are going underneath buildings, so heavy coordination between really everyone on site, but especially the foundation contractor, the structural engineers. I think we might be doing another test well on this project just to maybe to reduce the size of the footprint of the bore field, see if we could get deeper, because I think we've only did 500 feet. This was prior to that law change that I think Griffin mentioned. It was about this time last year, maybe a little less, where you no longer need to permit with the Department of Mineral Resources if you're going to go beyond 500 feet in New York State. So we're looking at possibly increasing the depth of the bore field we're working on here. And this also includes sewage heat exchange. I don't have any good pictures of it, but a shark-type system where, so this will be using solar. It's not net zero, but it's going to have solar, geothermal, and sewage heat exchange. So this is an exciting one that's going to take a long time. This one, I might skip this one. That one as well. This is, I guess, what we're really, this is a good one because it's Fordham. I think this might be an old presentation, so I know it says 940,000 square feet and 10 buildings. We're now working on a project with Fordham at their Rose Hill campus, so not this campus, it's up in the Bronx. And it's 2 million square feet and it's 28 buildings across 3 districts currently we're planning. And it's all retrofits. There's no new buildings going up, so there's no boreholes under buildings. They have a big campus in the Bronx. I don't know the total acreage, but I know one of the first districts is 22 acres. They're literally on site surveying it now, so we could figure out where we could put distribution piping, where we could put new plants, and where we could drill all these boreholes we need. So it was cut pretty short, I suppose.
Yeah, we apologize. We actually provided a new Fordham presentation that didn't get uploaded. So I could talk what we're up to on the Rose Hill campus. since we don't have our maps. So we're working on 3 districts at the Rose Hill campus. We have the athletic district, the Martyrs Court district, and then the south type district. Interesting thing is the athletic district is very heating dominant. They have an auditorium, they have their gymnasiums that they don't cool, so they have a lot of buildings on that side of the campus that they heat. The Martyrs Court does a lot of residential, it's got the library, some academic. We have a large cooling load over there. So in our initial Martyrs Court, that we're actually doing more concepts right now, schematic design, we're developing a central plant that's gonna make hot water, chilled water. It's gonna serve about 10 to 12 buildings in the Martyrs Court area. What we're looking at is, which is traditional for our company, we typically convert campuses, academic campuses, not industrial or pharmaceutical, but academic campuses, about 130. And the reason we do 130 is when you have a lot of residential living, we actually will then do instantaneous water heating for all the domestic water. We do a couple double plate frame heat exchangers. So it's a nice way to pick up 100% of that domestic water. But then also we can actually move our energy around as the students leave the resident halls, go to that academic. Our equipment doesn't have to be sized for that peak load. It's actually a well-diverse load where we can really downsize our equipment. And then we're looking at doing an ambient loop that will connect into the athletic district so we can move our excess energy from Martyrs Court. We're gonna move all that extra heat we have over to the athletic district to heat the pool, heat the gymnasium and the facilities over there. And then we're gonna complete our ambient loop in our study to pick up the southern type buildings. Now, when we do campus conversions, folks, 50% of all the first cost is building conversions, because typically they're either a steam building or steam heat, radiators, coils. And some buildings actually have a shell and tube heat exchanger, steam to X water temperature, 200, 180, right? For us to convert those buildings down to 130, 120, 110, whatever it may be, it takes a lot of time and money. So we may then put in a high lift heat pump at that building level connected into our district system as our energy source, and we'll lift just that one building to 180 or 190. It could be a recip type compressor, a screw compressor, whatever it may be, to give us that extra lift that we need. And the key there is you don't jeopardize your whole campus, right? Your plant doesn't take the whole hit to make that higher water temperature. Especially at Fordham, a lot of their buildings are 2-pipe switchovers. They're already been set up for a low water temperature, campus distribution. They can easily heat their buildings probably with 110-degree water because the switchover, they're all cooling coils in the fan coil units. 4-row, 6-row coils, perfect for a low water temperature. So we don't want to jeopardize our high-efficiency new plant for just a few outlying buildings. You're best then to put in some spot high-temperature lift heat pumps, pick those buildings up. I think that's probably covered of Rose Hill. Thank you. Appreciate it.
Appreciate it. Audience questions? I have a couple, but please.
For the ground source, 2 questions. One, have you guys seen any community level ground sources? The upfront costs are so high. Have you seen a lot of community willing to dedicate an area, perhaps like a sports field, great baseball field, soccer field?
Yep.
Anywhere like that, and actually have it serve the community on a limited radius basis, obviously. And then the second part of that question is, have you seen any issues with the open loop ground source where it's actually eroding underlying structural integrity of, sediment and
Sure.
dirt?
Sure. So the first question about utilizing an ambient loop to serve a district multiple type facilities, residential, maybe mixed use, whatever. Yes. One of our first ambient loop systems has been up in operation now 2 years, up in the Toronto area. That's a single pipe ambient loop, and it picks up, I believe, about 500 facilities. And we have multiple ground heat exchanger injection points. So that's the key on an ambient. When you look at a district ambient system, if you could do a one pipe or two pipe, right? We've been doing two pipe forever. I would say the single pipe has been more of a newer application, especially for our firm. It's becoming more, I would say, popular right now. We're doing a lot of these pilot projects. So you're seeing a lot more ambient one pipe systems picking up commercial, residential, mixed use type buildings. The key with the single pipe though is really all your injection points, because you want to try to maintain that water temperature in that one pipe. I remember back in the day when we did steam systems and we did the monofoil fittings. You guys all remember those? Right? So we'd have one pipe and you'd have a monoflow. That one would pull off and put the energy back in, right? So we're all used to a single pipe application. They've been around a long time. And we're just using it now in a whole different application. We're not doing monofoil fittings, just close couple T's. But it's really about where you're injecting the energy and what is the allowable water temperature drop in your pipe. So especially in heating, you can't allow your temperature to get too cold, right? Because my next heat pump over here won't have enough energy to pull from, enough lift. So that's the key, is what is my water temperature drop that's allowable through my whole one pipe ambient system. It's starting to get too cold, we have to then inject some more energy here to pull that water temperature back up. Okay, so it's a great application, just got to really understand how do you size that one pipe and the flow rate. We don't want to overpump, because then we wasted all our energy savings with our heat pumps by burning up all our energy savings with oversized pumps. So it's that chicken and the egg, right? Second question, open loop. Our company has been doing open loop for 30 years. We're probably designing one of the largest open loops right now. It's 21 wells. It's on a whole campus setting. We have 7 supply and 14 re-injection. Okay. So you don't erode any subterranean or your formation, because when you pull that kind of water out of the ground, right, we're pulling about 6,000 gallons a minute in this site. You got to watch your water velocities, right? So we don't want to erode any of our formations. We want to make sure it's a long life cycle, that this water-bearing zone provides us this kind of energy for the life of our system. So yes, you got to be careful on the supply well, but also the re-injection. And that formation there, we need 2 wells for 1 supply to handle that re-injection. Otherwise, it's just going to mound because the formation doesn't absorb it. So.
I have a question about a related issue, which is whether you've ever seen excess well capacity that has been installed but is not actually being used. So like an oversized system, which must happen, even if your firm doesn't do it. But later in a separate project down the road, once you've actually gotten the real metrics for the building in operation, you see that it's not using the full capacity reliably. Have you ever seen that extra capacity later used for an expansion without having to drill new wells, or perhaps for a neighbor becoming a district, maybe not even the same owner, things like that, where you did oversize, but it actually saves money in a later project?
Correct. I've seen it both ways. I've seen ground heat exchangers very undersized, and then I've seen them oversized. It's better to be oversized than undersized, right? You can do a lot with your oversized ground heat exchanger. You can, like you said, add an expansion. One of the newest things out there in our industry, right, is people want to sell their energy. So I'm going to sell my energy to my neighbor, right? We're creating these energy networks, and they're trying to get these laws changed that you can become a utility and sell that energy, or you can, through a lease program or whatever. So, yes, an oversized ground heat exchanger is much better than an undersized, and you got opportunities to expand or do multiple things with that ground heat exchanger, or your heat pump's just gonna be, right, much better performance, your COPs are gonna be very high, and your power is gonna be reduced.
So on that point of like markets to share this surplus energy that's being generated, are you seeing any of that with geothermal? Because with battery storage, we're seeing virtual power plants. You know, you get a power wall or a similar residential or commercial storage. The manufacturers often have a virtual power plant that is just interneted together, and they can reduce load from peaker plants in their contracts to be paid. Are you seeing that using geothermal as a resource in an actual market?
Yes. There's a lot of pilot projects out there with your utility companies. They're all trying to get into the business now, right? They see the gas business is being reduced. So they're out there building all these pilot projects and owning them and providing that energy to their customers. We're also seeing where there are many companies out there right now that are trying to do these P3 programs where they're gonna come in and they're gonna own and operate either the heat pumps or maybe just the ground heat exchanger, and they're gonna create that network and sell you the energy that the ground is providing. A lot of different financing programs out there, you know, that our industry is getting into. It's new to our industry, but it is expanding.
So what was entirely a cost can now become a profit?
Yes. Yeah. A lot of our commercial industrial clients that are in this, they're not interested in selling their extra energy, but they could, but they're more, you know, utilizing the efficiencies on their own.
Thank you. We're gonna hold questions, right? We're gonna hold questions. Hopefully we have a little bit of time at the end, but a lot of geothermal and heat pumps, huh? Wow. Right. I tried to bring some solar in. I couldn't find a lot of major projects going on in New York City. But if there are technologies that we haven't hit today, we want to hear about that. We want to hear about what the audience wants to hear about, and we will produce that content for you, okay? But what I'm hearing about is a lot of over-design and under-design, tremendous amount of balance is needed in making these systems effective, efficient, as we plot our way to net zero, which I would think means we're going to need a lot of data. I was very impressed with the idea that they're stringing sensors all the way down the well to see what the gradient is. But what are we going to do with this data? How are we going to analyze it? And that brings us to our next presentation by Jean-Simon Venn. He's all the way here from Canada. He's the Chief Technology Officer at BrainBox AI, and hopefully he will enlighten us on the information age. Maybe we call it AI 2.0. So, Jean-Simon.
All right, thank you very much. All right. So good morning, everybody. Actually, it's afternoon. So the AI angle, how can we use AI, artificial intelligence, to decarbonize? Learning objective first. I want to demonstrate how do you deploy AI, how much does it cost, what kind of benefit it will generate. But more importantly, at the end, we're going to really look at a very concrete example in a building here in Lower Manhattan and exactly what it did trigger in terms of benefit for the building operator, the building owner. So just going to give you an overview of how do you use AI. I'm going the entire slide here. The opportunity really lies in the fact that there's already in commercial building a controller which is digital and basically generate a lot of data, to Scott's point. That data is used by the control sequence to operate all of the HVAC equipment and make sure that the building is properly operated. So the opportunity for us was like, wait a sec, we're gonna connect to that building controller system, and we're gonna extract that data to see what else can we do with it. So most of the cost of the AI deployment project is connecting to that controller, and as you all know, some of these controllers are not that easy to connect to. Getting the data out, cleaning the data, mapping, tagging that data so it could be used by algorithm or deep learning. I would say, like, in typical project, we're looking at a 3 to 4 months payback project, and I would say like 90% of that cost is the cleaning of the data, the tagging of the data, and making sure it's accurate, that remove all of the outliers. So we then use that data to train deep learning models, which are giving us what? Well, deep learning is really giving you a prediction. And this is the byproduct we're getting from using deep learning neural network, which are giving us a prediction up to the 6, 7 next hour, what will happen in that building. So we kind of see the future. We see that in this room, in 3 hours, it's gonna be too hot. The system will trigger, will do what it has to do to maintain the proper temperature in that room. So interesting, we did actually publish a couple of papers about it to see how accurate we were on that prediction. But beside the scientific excitement, really, it didn't create any value for the building owner yet. Then what we've done is we really looked at ASHRAE 36 guideline. And we designed these virtual robots, which are basically just applying the ASHRAE 36 guideline to the letter. Actually, there's one which is the ASHRAE 55, but that is a separate topic. And basically, these robots, they're using the prediction coming from that neural network, and they're trying to figure out, how should I operate that building in a better fashion? And they do that in real time. That's what AI is very good at. So let's dive a little bit about what do I mean about prediction. So a neural network, to be efficient in prediction, you need to feed it a lot of information. So of course, we feed it all of the trend data that we're capturing in real time from the controllers in the building, and we're adding a bit of other ingredient in the sauce, like, of course, the weather forecast, and some other information that is readily available on the internet. It could be Google Popular Time, which is telling us how busy that restaurant is, or equipment spec sheets, or ASHRAE guideline, which could be also interesting. And we're getting a prediction. And the quality of the prediction is actually the most important thing at BrainBox. We're always monitoring that quality. And we're not so much interested for the next 6 hours to know how much the two curves are overlaying, what we predicted and what really happened when you let it rip, but we're much more interested by the change of direction. So the temperature will climb, and at what time will it basically change direction and decline? And the other thing which is quite interesting is at what speed is it going up and at what speed is going down. These are really the two important information that the algo, the virtual robot, will use to figure out what should they do to change that future. So it's really a bit like the movie Back to the Future, where we see the future, so we go in the future, we see, oh, not good. Then we come back in the present and say, what can we change to change that future for a better future? What can we cancel out in terms of events which are not desirable? So before I show you what it means and how does it fit in the existing control sequence of the building, AI, to bring value, it needs to understand how to win. It's really why you should not play against it in any video game, because it really likes to know, how do I win? Very basic. And the way we explain to the different virtual robot how to win is multiple objective. So we're telling the virtual robot to win the game, because that's what they want to know. That's the only thing they want to know. How do I win? I need to reduce emission. I need to reduce quantity of energy being consumed, which is going to have an impact on cost. I need to reduce cycling of equipment. So if there's a way that you could obtain also reduction of cycling, we know that somehow that's going to help the lifespan of that equipment. So these are multiple objectives, and of course the comfort. So try to maintain the comfort in a better fashion than what you were going through today. Okay, sorry. So what it does then, I lost my screen, I got my screen back. What it does then is these virtual robots, they're looking at all the control strategy. Very basic, right? Control sequence. They're looking at if I do this, what's going to be the future? If I do this, what I'm going to future? So here's a simplistic representation, only 7 control strategy. In real life, this is what it looked like for each zone. So you've got a very large quantity of option on how can you operate that building on a different control strategy. Those are basically the black line. But there's only one, the yellow one, for each zone, which is giving you the optimal control strategy to really reduce all of your objective to as low as possible. So, and that is what is happening every 5 minutes on the air side and every minute on the water side. And this loop goes in, analyze, try to figure out what's the best strategy, and then decide the best strategy, make the move right back to the system. And then what's really happening is you're flipping from a reactive control, which is what the existing control sequence is doing. Existing control sequence is notifying that, oh, there's a start of a trend that I don't like. I'm going to react to it and make a correction. Preemptive control is, I know there's going to be the start of an event in 2 hours. How can I do something now to cancel out that event? And the two really goes together. So we don't suspend the existing control loop. It's still at its place as a safety. The preemptive control loop is happening hours before, or sometimes 15 minutes before, and it's trying to basically make sure that the existing control sequence does not trigger. And if it fails somehow, don't worry, because the existing control sequence is always there, always doing its thing. And then you have these two control loops working at a different time on that time scale. So I spoke about this. So let's look at a very specific case that was done in Lower Manhattan. The building, 32 floor, typical configuration, condenser water plant with 32 air handling unit. It's a Schneider Electric EcoStructure, so we were lucky there was a proper control system. We were not in one of these buildings with pneumatic system, where right at the go, there's nothing we could do, as you could imagine. To Paul's point this morning, they don't have a water fountain, they have a waterfall. And a very nice pound full of fish at the bottom. So definitely, Paul, I'm probably going to send them an email this afternoon saying, what about? And you don't need AI to do this. We just shut it down and put, I don't know, plants or artwork instead, because I got your message. These virtual robots, and you're going to see these names, there's 15 of them. They all have weird names because the philosophy at BrainBox is whoever engineer design a new virtual robot, it's got to find a name for it. So we ended up with all kind of name, which is driving the marketing department completely crazy. So in this example, we were able to select 2 virtual robots, Optimus and Water Clock. We always limited by how many can we deploy on the point we have access to, either in reading or in writing back. So that usually decide what robot you could deploy in that building. And as you all know, we're not living in a perfect world, so that is always a limiting factor. Optimus is really using predictive to figure out what is your best startup strategy in the morning if you have occupied and unoccupied kind of framework. But most of the savings are coming from the gliding at the end of the day. So we're really not talking about optimal starting. We're really talking about optimal gliding at the end of the day on using your thermal mass, and at what time should you really keep running your fan, but you could slack the cooling or the heating and try to harness some saving. Water clock, name says it. We're really focused on the water. So how much water, how much cooling should we produce? Remember, we know what's coming up in the next 6 hours. So we could start to really optimize the COP on the water side because we know the future. So what it gives us, it's we started to deploy in August 22. And the reading that I've got is all the way to October of last year because we're kind of doing the MMV twice a year. So right now they're doing it to see what happens since October. Optimus Prime was deployed pretty much for the entire period. Water clock was really commissioned in August and September. So you only see the end of that period. You see the impact of water clock. but already you see that saving happening and that 228 metric ton of CO2 save, which is most of it on Optimus. And I'm going to show you what it's looking at on the projection, about 787,000 kilowatt hour, just above 100K of saving in dollar. And this is basically how it's saving. So as a start, and you really see the impact, and I don't see if I, no, oh yeah. You really see the impact of water clock that was put in production here. So this is pretty much all Optimus, and then water clock was put in production here, and you see the trend happening. So we cannot wait to see what's the impact following this. And what I will show you here is how interesting as AI is having a different impact, right? Because the AI is looking at the building as a global equation, not just, even though each robot is really operating at the equipment level, the global goal here is to optimize the building as a whole. So you see is what's happening is the AI like consciously decided to increase in some period the fan spending. So it's costing more on the fan with BrainBox than without BrainBox at certain period of the year. But it was basically going and getting a lot saving on the cooling side. So it's transferring energy from one equipment to the other one because the global equation is what we're after. So sometimes customers, when they look at the trend, they go like, whoa, my fan is working harder than before, guys. Should I worry? And we go, well, you have to look at what's happening on the other side. Then you're going to start to have a global view. And once again, I want to attract your attention here. What happened when water clock kicked in? It was a huge impact. And basically, I'm going to skip the slide. Everybody's going to have access to the slide. I want to show you why. Well, basically, water clock did its trick on the COP. It really made a huge difference as soon as water clock started. You see the COP increasing by 90%, and really the energy basically coming down to a level which is quite interesting. So of course, it's something that could be done by pretty much all of us with a good Excel sheet. We're going to figure it out. The problem is this thing is doing it for a few pennies on the dollar compared to our own salary. And the second problem is there's not enough of us to do it for the entire building stack. So there's no magic with AI, really. That's the key message I have to retain. It's just calculation being done and guideline that we all know, but being applied to the millisecond and at a capacity that you could scale. So we don't need to put somebody at each building to do continuous commissioning and do that calculation. It's happening by itself, and it's following the guideline that we decided to be followed. So that's pretty much, Scott, I think the question will be shared.
That was really intuitive. Any questions? Yes?
Thank you. That was very good presentation. It seems like the samples you're getting are emphasizing lowering the overall energy use. Have you guys looked into starting to apply finalization on non-fossil fuels versus just overall reduction of energy?
Yeah, you're right. We were basically on the cooling side only on that building because that's what the customer was asking us to start with. But definitely the heating side will be quite interesting. One thing that we notice when we're doing the fossil fuel side of it is the AI tend to pay too much attention to it because the multi-objective is saying, please reduce my total energy spending, please reduce my total emission, while maintaining the comfort, while reducing cycling, automatically the AI goes like, wait a sec, if I go on, let's say on the natural gas side, I'm going to not only reduce total energy, but I'm also having a super big bang for the buck on the emission side. So we have some time to put some weight factor to lower that kind of excitement, so we don't have an AI which is focusing only on the natural gas side and not caring anymore about the electricity side, especially when the electricity is coming from a green source. So we're using WattTime. I don't know if you're familiar with WattTime. That's NGO in California. They're giving us in real time through an API how the electron that's coming in that building, and you have to give it the specific address, was manufactured. So we have that in real time. We basically know that the electron coming in that building right now was manufactured by a nuclear plant, by a coal plant, by a solar panel. And having that information is super important to give back to the AI so the AI could have a proper judgment. Because indeed, I mean, if it's coming from a solar panel, maybe it's okay, right, as a kilowatt hour. If it's coming from a coal plant, it's actually worse than natural gas, so okay, maybe I should focus on that instead of the natural gas. And that's quite an interesting check and balance that is happening in between the different virtual robots.
Question?
I'm sorry, I just asked to repeat the question when you answer it. Thank you.
Larry?
Yeah, so,
Larry?
hi, great presentation, it's completely fascinating. My question is, what are the inputs that you're using for Optimus? And I'm just gonna assume it's temperature, humidity, and CO2, but can you elaborate?
Yeah, we're taking everything that we could get our hands on in that controller in the building. It's always a limiting factor. I like to say, and it's no finger pointing, but I like to say it's kind of a jungle out there, right? Because people don't really pay attention to it. So we have a lot of data that, yes, you could read it, but it's telling you it's 600 Fahrenheit in that room. So clearly it's a error on the digit, right? This would be 60.0, but that dot disappeared and we're receiving 600 Fahrenheit. You feed that to the prediction, you're gonna have a prediction that you don't wanna use. It's gonna be completely easy. So we have to be very careful to always monitor that data coming in. So we're taking all of that data because we could get our hands on from the controller, and then we're taking the weather, and I'm not sure if that's where you were going with your question, but we're taking the weather from the pilot. So the same weather that the pilot are using, yes, we are interested by the outside temperature and the outside humidity, quantity of water in the air, but what is more important is the thickness of the cloud, because that's usually a bigger driver to figure out. So the pilot on the all airline, they have that weather, which is basically the thickness of the cloud at any given time in a specific area. You have to be careful, it's a radius of 25 kilometer precision. So it could be on and off. So, but in general, it gives you a good feeling on the impact of the solar radiation at that given day or morning or afternoon for the building located in that kind of the 25 kilometer radius. And that's very often a key driver. We're getting wind direction, wind speed, wind gust, which are also sometimes, especially in Canada, a big factor regarding what side of the building you're on. So all these information are really feeding into the neural network and giving you that accuracy of the prediction that is so important. On the prediction, we could really tweak it the way we want, but usually we're very interested by temperature and humidity prediction, but we could basically tweak it on a chiller regarding the quantity of chilled water that will be produced.
Question?
Again, good question. I see the examples and they were focused a lot on the fluid side, but a little bit more bigger picture. The examples were high level when it comes to AHU. How efficient is this AI when it goes down to the zone level? And you know, what are your tagging methods? What does your data model look like? You know, especially on the zone level, you have a lot more equipment, you have a lot more stuff to tag. You know, so the semantic interoperability issue that we have with standardizing between different vendors and stuff.
Yeah.
How do you guys approach that?
Yeah, so we decided early on that the fundamental building block will be the zone, whatever it is. And the prediction is per zone, basically. So the problem, of course, we have is the way they define the zone. If they did huge open space, they define two zones, and really like it's, we're gonna get what we're gonna get, right? And the reason we took the zone as a building block is we figured that after that, we don't really care the size of the building because we really manage per zone. And then if you have two zones, let's say you're a Dollar Tree, because we're doing all of the Dollar Tree across North America, they usually have 5 zones if you count the office in the back. So that's, you know, pretty easy. But for us, we just aggregate the zones. So we're also doing Aéroport de Paris of Charles de Gaulle. They have 300 zones in one terminal. So then suddenly, for us, it doesn't make any difference because we just aggregate the zone. So you could have 3, 5, or 300. For us, there's no difference. Of course, there's more computing power happening on the side, but it's pretty much like the Lego block that you aggregate.
Carrie?
Going in the other direction of scale, I'm wondering if you are
I'm not sure I understood that question.
If you're working with like increase the buildings with the demand response provider as opposed to looking at individual zones, and are you considering can you increase the buildings because you have a really active approach to when you can use or not use energy?
Yeah, it's an excellent question, and I have to be careful because some stuff is not released yet. But yes, now we're working that really we started on the air side, then we did the water side, and then now we're looking at what happens if we aggregate. We have a lot now. We're about 3,000 buildings deployed. So we're reaching a level where we could start to build cluster in a given region and listen to what the grid would like to see in terms of behavior. So absolutely answering a demand response, that is coming up this summer. But I want to push it further out than that. Like, let's not just stop at demand response, but the grid should tell us at any given time what they would like to see in terms of profile. And we're going to build a cluster, which is going to be multi-owner, multi-operator, right? We can mix a Walmart with a Dollar Tree, with an office tower, with a college campus, and if they're in a given region which makes sense for the utility, you have that cluster built on the fly that will basically try to accommodate the constraint coming from the grid. So we're right now in discussion to do tests of that in places that I didn't suspect. I was expecting that to happen more maybe on the east, either on the California side or on the northeast side, but it's happening in Kansas. So I was a bit surprised that it's happening in these places. But there's a lot of discussion going there. It's moving at the speed of the grid operator, and I'm going to stop there.
Question?
Yeah, I'll just ask a question with your moving at a speed and kind of picking up on what Brandon asked about energy savings and decarbonization and your comment where how do you balance those? Last week, Elon Musk said that by the end of this year, AI will be smarter than an individual human, and within 5 years, then the whole group of us. Do you think in 5 years, your technology or some of your competitors are going to be able to give us 5 or 10% energy carbon reduction across a broad range of buildings? How might this go to scale?
Yeah, I'm not going to comment on Elon Musk's prediction because he's not always right. I don't believe we're going to have matching the human anytime soon. So I want to reassure you on this. When you look under the hood, at the end, it's a mathematic formula, right? Let's not pretend it's more than that. It's just capable to crunch so many numbers in a millisecond that we just cannot match it, right? It's the sheer speed of calculation. We're already, when you look at the different, like 3,000 buildings, we're already in between 15 and 20% saving. So we're already there. But the real impact is exactly what was mentioned in the previous question, is at the grid level. If you want to save the planet, we could shave a 20% across the demand of all the commercial building. It will not be enough. We need to go up the grid and have an ecosystem which makes sure that that coal plant does not start in the afternoon because they have to face a peak demand and they have no other choice than starting it. So how can you make sure that that coal plant does not start in the middle of Pennsylvania this afternoon? And that is where you start to have a really huge impact. So I think when we're going to reach that level, and it's all about the installed base, right? Then we're going to have, like, we're going to moving the needle.
Yes.
It's pure hell. Listen.
Why? Why is it pure hell?
Yeah, it's hell because people have been doing things a certain way for 30 years. It's working. People are happy in the building. It's comfortable. And then you're coming with AI, right? I think there's not a single movie about AI coming of Hollywood which has an happy ending, right? So what's happening is, if you're not like really familiar with how AI works, the first reaction will be, wait a sec. You want me to let that thing that I don't understand control my building, and if something goes wrong, I'm the one they're going to fire, right? So how do you build a trust? And there's a lot of education. So you have to explain, see how, of course, we provide that huge red button release. But it's only after months of usage that you start to have a trust getting in place, and looking at these graphs showing the value. And in every project, we start like sometime with one floor, one zone. Sometimes we start with one zone. They say, try one zone, we'll see. And you go slowly. In the case of the building that I showed you, we started with Optimus, and it's only when they saw the value of Optimus for 6-7 months that they allow us to deploy water clock, because we were building the trust. And there's no other way. That's the way that you have to help people to use a new technology.
Thank you. Elliot?
Once you've built the trust with the operators and they're using it and it's demonstrated its value for over 6 months, how is it changing their day-to-day tasks? Is it simplifying their lives, adding tasks? Do they like it? What's that like?
Yeah, so I have yet to, the question is, how does it change? I forgot to repeat the question, I'm very sorry. So the question is, like, how does it change the life of the operator when they start using it? No, we're not cutting the job. The person still have a job. Usually that position, you go at home at the end of your day and you've done about half of the list of your things that you were supposed to do. And you manage to extinguish the fire, but you always go home with the feeling that that to-do list is never ending and you were not able again today to finish it. So we're giving the extra capacity so you could work on a lot of other things that you never have time to work on. And then you start to increase the level of productivity. And you're also compensating the fact that there is a shortage of people that know how to do that job. And then suddenly you're kind of helping to resolve that shortage of people doing that job and at the same time increasing productivity. So pretty cool.
So, Brandon?
So building on the question of expanding to the grid level, have you started any conversations with utilities or other energy incentive providers to create like an AI incentive? And the thinking behind that is, I know at least for when there's still a lot of interest in gas, right? There was a service called interruptible service, meaning that the building would get the incentive of a lower cost per therm. But if the grid said, hey, it's a very cold day outside, we can't get you guys, they would have a backup at the building, but they would not get the service. Switching that to the electric side using AI, if the AI predicts, hey, we're going to have an issue with demand, and it knows what components in the building are able to go down temporarily for an hour, right? That would be a big advantage to the grid as well as the users. Has the utility started to think about offering lower per kilowatt hour rates for buildings that participate in the AI community type of program?
So, I don't know, should I repeat that question?
Are buildings incentivizing, are buildings being incentivized to move towards AI strategies?
Thank you. All right. So the quick answer is no. I mean, I don't know of any utility that has started to go there yet. Are we talking that kind of scenario? Yes. We're actually working with National Lab in Berkeley to try to influence that discussion. And we want to do a test with them to demonstrate. There's also what I mentioned in Kansas that is happening, which is going to be an interesting test. There's another test happening in Australia. They have all kind of problem in Australia regarding the grid. So this, I think, is going to help evolve the discussion, but unfortunately not yet. What probably is going to happen before that is the integration of solar panel, the integration of batteries. How do you manage the battery? How do you reroute the kilowatt to the battery to recharge that car, to the chiller? When should you do it? So how do you manage the thermal battery of the building to help charge more vehicle, and when should you do it? And that kind of a huge problem that is starting to hit us. So that's probably going to be, I think, the entry, the door that is going to help us having that kind of discussion that you're outlining about. Well, it's going to need to have a discussion on the rate and how much do I charge when. to help everybody on board, right?
So we have two more minutes until 1 o'clock. We can stay a little longer in the amphitheater. We're serving lunch outside, so if you're hungry, please feel free, but if you want to stay and ask the panel some more questions. Just want to make sure that we're all scanning this bar scan so that you can get the 2 PDH credits that are allotted for the panel. And do we have any questions? Do we have any more questions? Yes.
Sort of a follow-up to some of the questions about reliability, and you said it yourself. These are just calculations and algorithms that can be done on an epic scale, much more than a human being can do in the same time frame. All calculations are subject to the folks that put them in there. If there's a mistake in the calculation, you're going to get meaningless data. I guess the question is, what's the fail-safe that's built into the AI decision-making process, number one, and what is it seems, you sound like an extraordinarily intelligent guy, and it seems like you know building systems to some degree, but some of the folks out there that do this work, when this takes off, are not going to be you. And the question is, how does the industry protect itself from early adopters from getting garbage calculations and then killing the whole idea when the building operators say, I'm never doing that in my building?
No, very good question. And trust me, we did create a lot of problem in our first buildings when actually in Toronto and Montreal when we deployed. Learning was a painful one. And I think there's customer that will never ever talk to us ever again. So it's part of the world of pushing a new technology. Think of SpaceX. How many times did they crash that landing before they got it right? Now it's good, right? So we basically took from SpaceX the same safety they put in place. They have 3 different computers which are looking at what's going on in real time with a different angle, philosophic angle. And these 3 algorithms, which are basically judges, they need to be anonymous. So the virtual robot are allowed to write back. So the virtual robot will not be allowed to write back until the 3 judges, which are looking at what's going on to their perspective, need to say yay. And they all 3 need to say yay at the same time. It's exactly the same system you have on the capsule of SpaceX regarding should we abort or not, should we launch or not. And it needs to be in real time. Because as soon as you put a human in the loop, you basically are destroying the speed, the advantage of the speed of the calculation. So it needs to be as powerful as the calculation itself to be able to make a judgment call. So that's how we put it together, and now it's much better with that. But you're absolutely right. It's something you have to be very careful about.
I'd also like to mention to everyone there are 2 QR codes, and the first one on the left is the PDH credit request form we've been mentioning. So to get your PDHs, snap that. The other one is for our presentation evaluation form for our chapter to evaluate this event, and that is the main way we'll get all of your feedback. We've been doing this as our 5th year, and we will really appreciate your giving us feedback using that form as well so that we can improve this further for the next time. Thank you, but I did also have a question to report. Which is that you've been mentioning a few times that the AI, when like most automation, it doesn't just put people out of a job. Instead, it makes the people who have that job more productive and more valuable. And that's when the automation is done well, and that is necessary to be able to scale up what we do to all the buildings that need it, which we humans have not been able to do yet, and we're not going to be able to do without some kind of help. So thing is, a lot of these buildings that we haven't been able to reach, they don't have a BAS or any automation. They don't have sensors. So that is probably the large majority of buildings, including in New York City. There's very small penetration of that, single-digit percentage. So how do you apply the AI to a building like that? Do you install a BAS for the purpose of profiling the building, data loggers? Is it the kind of thing where you might put in just a data logger so you could profile the building and then that's it? You just then give instructions to the building operating staff? Do you use something like Energy Star Portfolio Manager, which New York City has a law that's shoving everyone into that, which has been great. but that's a data repository that has its own constraints. And if you have to do some of this augmentation, how does that affect the ROI? Because that's extra, and your AI has such a great ROI without it.
Yeah, so usually the control contractor, they like us because we basically, our answer is you should install a controller, so whoever is your contractor, please call them. I'm sure they're gonna gladly give you a quote. So that's usually the way it works for larger building. For smaller building, if it's like say rooftop, and there's a lot of rooftop in the United States of America, it's about 70% of the commercial building stack. And still, they don't have, most of the time, especially the small one, BMS. The way we go around it is we recommend that they install like a Wi-Fi thermostat. So they flip their typical old thermostat with a Wi-Fi thermostat, and there's several providers of these thermostat. And then we basically create that synthetic connection, getting the 6-wire from that rooftop connected to that thermostat, shooting that information, and we could do command control. So that's the way we kind of go around it. And let's say, give you an example. In Canada, we'll be a sleep country. So all the sleep country were done like that. The Gulf town were done like that. In the United States, Tractor Supply. So it's kind of an easy way to do it without spending too much money. But still, they need to spend money, right? Unfortunately. And of course, at that point, the payback goes from 3 months to much higher, right?
So even a small amount of data that isn't like a complete picture that you would otherwise use to control the building, nevertheless, the AI can use something and make improvements.
Yeah, the AI will do what it can with what you give it. So we're always limited by the quantity of point we have access in reading and quantity of point we have access in writing back. And sometimes like a customer will tell us, I don't want you guys to write back. I'm just going to give you reading authorization. And I go like, okay, but I'm not going to give you any value because you need to be able to write back to basically create some value. And right there's sometimes a lot of education to do.
Yeah, I have a question. So, in terms of the AI, once you put together some type of predictive analysis, does that automatically then update the sequence of operations or overwrite it? Or does it send a notification to the building operator to make those changes that you're recommending? And also, are you able to see maybe if the sensor is malfunctioning in a specific zone and kind of give them an alert, like, hey, this is broken and I need to replace that?
Yeah, so there's no human in the loop. So when the virtual robot, they take a decision to write back, they're gonna open that damper, they're gonna increase the fan speed, and they're not asking the human if it's okay, they're just doing it. Of course, the human could monitor what's going on. The problem is that this is happening so fast, and the human does not have the prediction. So it does not understand why are we increasing the fan speed right now. There's kind of no point. Why? Because we're probably canceling out something that's going to happen in 20 minutes, but of course you don't know that, right? So it's kind of hard to follow as a movie until you see the end when you start to understand, oh, that was a good strategy, but you have to wait until the end of the movie. Your other question was... Yeah, so we're working on that now because there's a large customer with a W letter that asked us, that said, yes, energy saving is very important, but we would like to reduce the truck rolls because they do send the truck roll way too often for a false reason, right? And that costing them a fortune. So, and of course there's a decarb strategy behind that because if you don't send that truck roll, of course you're gonna decarbonize, right? That's what we're working now, try to give them, using the same data and see if we could have a virtual robot giving them that information, should they or not send a truck roll.
Fantastic. That's fantastic. Some of the panel members need to check out of their hotels and get to the airport. So if you have a question, just email us. We're gonna get together afterwards. So we'll work on your questions. I really wanted to thank the panel. Each and every one of you, Jeff, Sarah, Griffin, Randy, Jean-Simone, and Richard. Also the presenters, Carrie, Paul, and Ginger is left. She's headed to Madrid to the Decarb conference. We really value the audience's opinion here. Was it good content for you? Were we missing some content that you expected to hear when you signed up, right? Was it at the right time? Was 7:30 a little too early to get you here? Is Monday the best day for a two-thirds day event? Your feedback is really invaluable to us. We're going to have an Earth Day 2025 next year. We want it to be as and more successful than this, so we really would appreciate your input. Once again, I also want to thank all the ASHRAE New York staff, and especially a thank you to Matthew. He's been grinding with everybody, dealing with me, all the presentations. We apologize to the panelists. Some of their last revisions didn't get in. Matthew, even last night, was battling with Fordham to try to get them through, so thank you, Matthew. And thank you, everybody.